give it one more minute. In the meantime, good morning, everyone. Welcome to Thursday's session of TQC. I hope wherever you are, you're keeping safe. And I hope you have a cup of coffee or your favorite beverage, depending on the time zone. And so our first talk today will be by Elena Kirshanova from the Immanuel Kant Baltic Federal University. And Elena, are you there?
I've just unmuted myself. Hello, everyone. Do you hear me?
Hi, yes, we hear you. We cannot see your screen or yourself yet.
I will start the video now. Yes.
Okay.
My screen. I can share my screen as well.
You can share your screen. Okay. So Elena will tell us how quantum computing can help us find the shortest vector problem, find the shortest vector on a lattice, and there you go.
That's correct.
Okay.
Good morning.
Floor is yours.
Good morning, everybody. Thanks a lot to the organizers for the invitation. I'm really happy to share the work I've done with my colleagues. And I want to tell you basically what I'm doing and what I've been doing since my PhD is doing cryptanalysis of lattice-based constructions. And most of my work is dedicated to classical algorithms. But since these lattice-based primitives and lattice-based cryptographic constructions believed to be quantum secure, it's also people usually interested in how quantum computers can speed up cryptanalytic algorithms. And this is what I'm going to talk to you about, is how we can speed up cryptanalytic algorithms quantumly. And we should not expect to have a large speed up. Well, otherwise this whole lattice-based crypto wouldn't be called post-quantum. So I've got instructions that questions will be asked afterwards. That's why, but I guess I could also take them as they go. Well, I don't know whether this is allowed or not. All right.
Sure,
so
sure,
this is
like if
there's
a question, I'll start.
Cool. So what is a lattice? I do not assume that the audience is familiar with the lattices. So I'd rather start with the definition. And the definition of lattice is pretty simple. Basically, a lattice is as a mathematician would say, this is a discrete, finitely generated additive subgroup of Rn. Alternatively, you could say that a lattice is a integer linear combination, all integer linear combinations of a basis vectors that are denoted here by BIs, and these are linearly dependent vectors from Rn. And there's usually n of them, in which case we have a full rank lattice. So basically, a lattice is an object which is infinite but finitely generated, and we can compactly represent it by a basis. Also, usually a basis, at least for cryptographic constructions, a basis is integral. So, example here is a two-dimensional lattice generated by a basis B1 beta. But of course, this is a two-dimensional lattice. We will be interested in high-dimensional lattices. For a lattice, we can associate several other definitions which will be useful for us. And the definitions are, so the first one is a minimum of the lattice. And the minimum of the lattice is a norm. And by norm here, I will always mean Euclidean norm, A2 norm, which is a norm of a shortest non-zero vector in the lattice. So for instance, here, the shortest non-zero vector will be V. And notice that this is not a unique vector because minus V has the same norm. Now, it's always good to have some bounds on what this shortest vector, what this lambda1 would be. And we have an upper bound, which is typically pretty tight, which is due to Minkowski. And Minkowski tells us that given a lattice represented by a basis, we can bound its first minimum, lambda1, this means first minimum, by this quantity, which is square root of the dimension times the determinant. And the determinant of the lattice is just a determinant of the matrix generated by a basis column-wise. So basically, this is all definitions we need to get to the problem. And the problem is the following. The problem, as the title says, is the shortest vector problem. This is the most important problem in crypto, in lattice-based crypto, but not only crypto. And this problem asks to find this vector that achieves the shortest minimum, that achieves the first minimum of the lattice. Now, we can also relax a little bit this problem by asking an approximate shortest vector. An approximate shortest vector would be a vector which is close to be, which is somewhat short, but not the shortest. So, and for crypto, we would say that gamma, it would be fine for cryptanalysis to find an algorithm that solves this problem for polynomial gamma, for gamma polynomial in the dimension of the lattice. So what do we know now about this problem? Classically, so first of all, why this is important? It's important because there are various reasons why it could be important. For me personally, it's important because all known lattice-based cryptographic constructions rely on the hardness of this problem. So if this problem is not hard, maybe we don't have lattice-based crypto anymore. Now, regarding the hardness, the exact hardness of SVP for complexity theory people, this problem is also interesting because this is an NP-hard problem. And it's NP-hard for approximation factors which are less than polynomial. So 2 to the log 1 minus epsilon n for any constant epsilon greater than 0. This is a less than polynomial. And this is an NP-hard problem. And crypto it's not based on NP-hard regime. This for crypto we assume hardness of SVP for small polynomial gamma. Let's say n to the 3/2 or n squared. This is what typically we assume. So what does it mean in numbers and figures? If you look at standardization candidates or proposals for lattice-based cryptographic constructions, they assume that it's infeasible to solve SVP in dimensions starting from 350 or 400 or something around that. I've not checked all the candidates for standardizations, but those I've checked, they are kind of assuming that we cannot, in a reasonable time, solve SVP in these dimensions. Now, this should be compared with what we can do now in practice, classical algorithms. For that, we have a SVP challenges with cryptanalytic algorithms should be solved for some dimensions to actually get the idea how hard it is. And if you can go and check to TU Darmstadt's SVP challenges what we can do, and you'll find there that we can now solve an algorithm, the SVP problem with dimensions 170, and we need a lot of RAM and a lot of GPUs to do that. So the term of the definition of we can also means that we have lots of we have heavy machines to do that. And if you want to try it yourself on your laptop, you can also go and download an open source library, which is called Jessica. This was my other project, classical, this time that and practical, that implements some of the algorithms for SVP. Now, for this talk, I will not be speaking about exact hardness, but I shall be rather speaking about asymptotics. And this is what we try to improve using quantum algorithms. Now, for asymptotics, the picture is not of hardness of SVP, the picture is rather complicated. And I have a recap of these algorithms here on my slides. And these running times that I'm going to present you, they work for SVP with approximation factor polynomial or less. So there will be two columns, classical and quantum algorithms, and they basically are separated now in two big families. The one family, what's called enumeration, and this family has a family of algorithms, has running time which is super exponential in the dimension. So here I'm going to writing the logarithms, and the logarithm of time is n times log n, with a constant in front, which is 1/2e for classical versions. Now this algorithm is basically a search in a huge tree, so it's a tree traversal. And quantumly recently it's been analyzed using backtracking algorithms to traverse the huge tree, which gives a square root speed up. The square root speed up in the exponent translates to 1/2. Now, a nice feature of these algorithms is that they require only polynomial memory. And this family is known to have a large running time, which is super exponential, but they are very memory friendly. Now, another big family of algorithms, they actually have single exponential runtime, but they also have exponential memory. Now, one of these algorithms, what's called they're based on discrete Gaussian samplers. And classically, they achieve the running time and memory of 2 to the n. So I write 1 and the bit in front of n just to emphasize on the constants. Now, because what you will see next is the change in the constant. Now, what I'm also not describing here is the small o factors, which are polynomial or even sub-exponential. We're really interested in analyzing this constant in front of it. These Gaussian sampler algorithms can be improved in terms of memory, but they become worse when we go to time. And what I want to talk about today is the other single exponential algorithm, which is rather a family of algorithms, which are called sieving. And these sieving algorithms, they come in two flavors. One which is provable, they achieve some runtime. The figures are there, you could compare them. And the most important, well, for me, the most important algorithms are actually heuristics. And you see the differences between the provable and heuristical versions. I mean, I believe that perhaps I don't want to overwhelm you with numbers, and it's not really meaningful to remember them. But the thing you should notice here is that provable and heuristic algorithms are quite far from each other. And they should also convince you that they're quite far from each other if you think that n is around 400. No? So if you plug in n around 400, then you immediately see that second or even the third digit after the comma will matter in terms of the bit security of the crypto system. No? Because the reason why we analyze this up to such a precision is that we want at the end at the end say how exactly this problem is hard for this dimension. No, and so the dimensions are big. That's why we actually want to make the constant as precise as we can. Now, if you look at the heuristic sieving algorithms, these are the last two. These are the last two sections in my figure. The best we can do now, and this stays up until today, is this classical logarithm time with 0.292 with the memory 0 to 1, almost 0 to 1. And this, I will explain how this algorithm works. And quantumly, the way we could speed this up is probably, you would say, not by much. And the best we can do now quantumly is the time and single expansion time, single expansion memory, both equal in the exponent to 0 to 65 times n. And I will also tell you how from these figures we can go on the right, from the left, we can go to these figures on the right. And what I've been interested in most of the time is how to improve the memory. And you can see that the memory, so when I say quantum memory, I actually mean that this is a classical memory, but quantumly addressable. So it's also otherwise known as QRAM, which is a model of computation. And some may argue that this is not a realistic model of computation, but this is where we analyze. This is the way we know how to analyze these algorithms, mainly because I would say one of the most used algorithms to speed up is basically Grover's search. And Grover does require, as a search over the database, it does require that we can access this database. All right, so what I will be speaking today is this last two parts, is sieving, what the sieving algorithms are, and how we can speed them up quantumly. Now I should also say that that time memory trade-offs is okay. There is a question. I guess I should take this now. Let's know if I even can do that. Somehow I cannot.
Yeah, I pressed it. So yes, so Mary's asked what heuristics means in the quantum case because we cannot run them, these algorithms yet.
So heuristics are for the analysis. So I will tell you once the analysis goes what heuristics are. Basically, heuristics say that we assume that vectors, so during the sieving process, that vectors behave in a certain way. So this is, so heuristics are for analysis. This is for analysis. For instance, one of the heuristics that we assume that that we do not. So okay, I will also say well what heuristics will be, and some of them concern analysis, some of them concern that we actually assume that the input lattice is sort of a nice lattice, so it's not orthogonal lattice, where we like some things go bad and go wrong. So this is what heuristics are, and I'll mention one of them, and they do not really concern the algorithm; they concern analysis.
Thank you.
Mm-hmm. So yeah, if there will be a question, I would be rather appreciated if someone will read it out, because somehow I cannot open this panel, and this is a known problem.
Yeah. Okay, I'll read them out. Don't worry.
Yep. Okay. Thanks. Right. So what is sieving? So sieving, probably you'll find this device in your kitchen. And sieving, basically, this device or the action of sieving means that you separate flour from dirt. Now, so the tiny small pieces of flour go through, and the larger pieces that you do not want to have, they remain inside. And this is basically the idea of sieving, and where we want small and short vectors go through and large vectors remain. What it means algorithmically is that we start sampling from our lattice we start sampling vectors, and sampling large vectors is not a difficult task. You can do it in polynomial time because you have a basis. You could, for instance, take linear combinations of your basis vectors with certain with coefficients from certain range. This will give you some vectors which will be probably long, but it will be efficient. And you put these vectors into the list. And I copy this list kind of in my head, because now what I want to do from this list is I want to find pairs that give me shorter sums of differences. No? Because a lattice is an additive subgroup. If V is in the lattice, then minus V is also in the lattice. So here in my picture, I sampled these orange dots, these orange lattice vectors. And I want to find between them something which, those that give me shorter vectors, shorter than those the original ones. So I'm going to do that, and I'm going to find these 4 vectors when I do the check. So I run through all of them, through all pairs in the lattice, and I go and I search for shorter ones. And I put them into a new list. So I find those and I put them onto a new list. And my new list L prime will contain the sum or differences of x1 and x2 from this list that give me a shorter Euclidean norm. And I repeat this process. Now I repeat this process, I copy this sort of list in my head imaginary, meaning I go through all the paths and in the hope to find something shorter. On my picture, because it's two-dimensional, I found it quite quickly. Now in high dimensions, you will need to repeat this process polynomially many times to find something shorter. Now the question is how large this list should be. And the answer for this is a very simple geometrical argument. And this is where our first heuristic comes. Well, first and kind of the main one, the only one I would say, is that we assume that all the vectors, when they're normalized, they are uniform. They are identically distributed uniformly on the sphere. Now that may sound a bit weird because the lattice is a very structured set, and now I'm saying that it's kind of on a sphere. But for high dimensions, this is what approximately you would see. Now you sample vectors in a certain way, and you kind of see that they all the length is kind of this, the norm is kind of the same. And this is kind of our heuristic that for high dimensions, everything is concentrated on the sphere. Almost all the length is concentrated on the sphere. And you could of course normalize it by the norm of the vectors to get a unit sphere. And so this is the heuristic that we have. In practice, this also should say that this kind of heuristic is a worst case, because if we have something shorter than the sphere, so if it's not like a sphere but there is a difference, like for practical algorithms this is even better, because longer vectors are highly to be reduced with shorter ones, but this we should not care too much about. Now what I want to say is how we can use that to analyze the list sizes. The list, we need to find something shorter. This is pretty simple. What you're asking is, what is the probability that the two vectors that I have in my sphere, they sum to something which is at least the same norm as these two vectors. And for that, you're just saying, oh, okay, I have the two vectors of length 1, they are on the unit sphere. What is the region? So I'm gonna say that this is of length 1, this is of length 1, and I want to find these two vectors such that they sum is something shorter or even the same. I can even be more generous and say the same, they give me the same difference, or sum as the length of the difference, or sum is the same as their length. Well, I could put here 1 minus epsilon, but for the moment it's assumed it's really the same norm. And this is basically just a probability that the two vectors on the sphere have angular distance or angle between them of pi over 3 or 60 degrees. Because if we have a triangle of 60 degrees, all the norm is of length 1. And once I have that, I have to ask the next question: what is the proportion of the spherical cap, which I denote here with orange area, relative to the whole sphere? This is also pretty simple to compute. The surface of this spherical cap is defined by the angle between the vectors that generate the spherical cap, and in particular by the sine of the angle. And the sine of the angle I want is pi over 3, because I want to be to become slightly shorter or the same length. So I'm saying 1 minus epsilon, and let epsilon go to 0. And this gives me the probability, or give you the fraction of this orange spherical cap on the whole sphere. Right. So, and then I'm going to say how many such spherical caps I need to cover, such that I need to find such that all the sphere is covered. So this will be the inverse of this number. No, so so the two vectors give me that, and how many vectors do I need to find to cover all of that? And this will be the inverse of this figure. And this will basically give me the memory. Now, if you come back to our algorithm, the analysis of the memory tells us that in order to start finding the short sums and short sums, you need to saturate your space with that many vectors. And after that, you will start seeing shorter sums or shorter differences. And this is, in practice, this is actually true. We actually do see this, that we need that many vectors and not much more. Now, in terms of the time, if we do it naively, namely if we do the search for pairs by going through the list twice, we would end up with the least square runtime, which is this running time 2 to the 415 times n. And again, I emphasize that I omit all the polynomial prefactors, such as the repetition time and maybe some concentration bounds that come from the sphere argument. But yeah, I'm interested here in asymptotics. And now you can start asking, right from this algorithm, what would be the quantum speedup? And any student who did quantum algorithms would say, okay, I can do Grover. For each x, I'm going to define a function that gives me 1 if f of x and y gives me something shorter. Now, if f of x comma y is x plus minus y, and take the norm, and if the norm is good, then you put this into then you mark it as a solution. Okay, you could do that, and this gives the first speedup, and the speedup will be the quantum time that requires, again, that much QRAM gives us the 2 to the 0, 3, 11 n as the runtime. It's a decent speedup, and it's not that we've gone much far from this pretty basic speedup. Now I want to say a few more details about this setup, especially in the view of the next. So today there will be another talk that speaks about closed vectors, and I want to emphasize that the specificities of this of the problem here is that note that we need to find that it's not, so the setup of this problem is that we need to find almost all closed pairs, so we can allow to drop a small fraction of them, but actually in order to repeat this whole algorithm, because we need to repeat this polynomial many times, we would need to find as many closed pairs, almost as many closed pairs, as the number of starting list. Now, because actually here the egg prime, the second list, in order to be able to repeat this whole process, it needs to be approximately as large, or on a asymptotic scale, it should be the same as L. So we can allow to reduce it by a sub-exponential factor, but not by an exponential factor. This is first. Now, the second thing is that the pairs we're actually interested in, they're much closer than those that are random ones. Now, on a sphere, you could, like the expected distance between two uniform vectors from the sphere, they're actually 90 degrees, so they actually are orthogonal. And what we want to find is something that is 60 degrees or less, and this is kind of an unexpectedly short vector, closed vectors from the list of random uniform random vectors from the sphere. Now, I want to briefly tell you how we can improve this runtime to 0 to 92, which is kind of the best possible we can do classically, and a quantum speedup of these algorithms is the best we can do quantum. And the way to do this is to use near-neighbor search. And the near-neighbor search is, in particular for this kind of distances, and this is angular distances because we're on the sphere, it's been known as the multi-sensitive filtering. And I use the word filtering as the proposals, the first proposals of this technique also do, because there won't be a function. There won't be a hash function. There would be sort of a region. Now, what I'm speaking about, the region, is basically this. Locale says the filtering, or you can also call it hashing if you want. It does the following. It separates our sphere by regions labeled with centers. Now, they have nothing to do yet with our list. And also spheres, they may overlap, regions may overlap, they may have some holes, but this is how we separate the sphere. And where the list comes, the list L comes, in which we want to find short vectors, short sums, we associate each element from the list to the centers. So note here that if two vectors end up in the same orange region, they're likely to give something shorter, contrary to the vectors that that end up different regions, that they're less likely to give something shorter. This is the whole idea of the Locale-sensitive techniques, that we want to improve the probability of getting a good solution. Now, note also that some of the vectors can end up in two buckets, which is in two centers, in two regions, which is also all right. And now the algorithm of finding close vectors that give something short is basically the following. We first do what's called the bucketing phase, where for each, where we associate to each bucket all our lists. And the second phase, we go through again through the list, but now we do not. So for each x, for each bucket, we look at this bucket. So we don't go through the list. We go through the buckets, and we look at it and say, okay, whether there is something short and whether what's inside gives us something short. So this kind of gives us a way not to go through the list twice, but actually go through something shorter than the list. Now, whenever we do the analysis that asks, that kind of tells how many of these regions there should be, what should be the size of these regions in order to find all the vectors, we'll end up with the following figures. Now, there are basically actually two kind of algorithms. The one which is sort of nice in practice, that tells us that we can speed this up using sort of random UIs, which brings us down to 0, 3, 4, 9. However, the best asymptotic result is obtained when the UIs come from a spherical code, and the spherical code gives you an advantage that you can find for each x all the relevant buckets in the amortized way, because the UIs come from the code, and you simply decode x with respect to this code where UIs live. And this gives the best known runtime, the best known classical runtime, and the best known quantum runtime actually comes from the fact that we can use a Grover over the buckets. Now, if you look at this algorithm, what you could do is that for each x, you could ask, give me all the buckets associated to this x. So give me all the buckets where this x ends up. And then I'm doing a Grover search over the content of those buckets to find the actually good pair for the given x. So Grover really helps in this part where we can where we do the search inside the buckets for a given x. And doing that gives us a slight speed up, or slight in figures, but maybe not so much in the view of cryptanalysis. Not so small is that the time and also the memory would scale as 265. Now this is sort of what we do. What we can do with it. What we can do now. Now, what I want to tell you next is, so this is kind of the state of the art for the runtime with local alternative filtering. And what we did with what we did last year is what can we do if we don't actually, if you want to save memory a little bit, if we want to save memory in the exponent. Now we can do several things, and I want to present you one of them. And I actually kind of happy to speak about it to this audience, which is definitely knows more about quantum algorithms I want to present next, or rather they use for these algorithms, is the following. So one way to save the memory is, instead of going for tuples, for pairs, we go for triples. So remember that previously our target was to find two vectors on a sphere which were close. Now we want to find a triple that gives us something shorter than the starting triple. Now intuitively that should improve memory, because there is simply more triples than pairs. For a given list, there is L cubed triples versus L squared pairs. But however, this would also intuitively increase the runtime. And this is true in both for classical and quantum algorithms. We have time memory trade-offs that we're looking for k tuples, where the k grows, we have more memory, but we save in memory, but we have larger runtimes. And for example, for triples, now if we look at the memories, that the memory reduces from the 2075 to 01887, which is in practice actually quite significant. Now you don't want to run in practice the algorithm that uses this much memory. Now, how we search for triples. One of the nice thing about triples or k-tuples is that you could try to analyze it in the same way as we did it for pairs. And once you do that, you actually notice that almost all good triples, and by good triple, I mean those that give us a solution, they're actually concentrated around a certain shape, and the certain shape is simply a three-simplex or a pyramid. Now, what it tells us is that all good triples, they have a fixed pairwise inner product, where previously for pairs, the inner product was 1/2. It's the inner product for vectors 1 with angle pi/3. Now, these guys, for triples, the target inner product of length 1 vector would be 1/3, or actually -1/3. And what it gives us a way to sort of filter out pairwise all these vectors in our list for good triples. And what we did in our analysis is we actually view this as a triangle search. Now let me tell you how. And the way we do it is we connect. Now remember that to find a triple, we actually only have to look at pairwise conditions between vectors. And the pairwise condition should be that the absolute value of the inner product is 1/3. And we kind of connect 2 points, imaginary in our head, or 2 vectors, if the inner product satisfies this constraint, namely it's 1/3. And what it means is that I'm looking at my pairs and I kind of connect them. I connect 8 and 7 because they have an inner product 1/3. I connect 6 and 5. I connect 16 and 5, and so on and so forth. And note that those triples, that all of them have inner product 1/3, they form a triangle. So what I want to say is I want to find triples where all pairwise conditions of inner product is satisfied. And by the concentration result, that would mean that these triples sum to something shorter. And okay, I guess people who do quantum algorithms say, aha, we know how to find triangles quantumly faster. And kind of yes and no, because when I started to look at this, first there are two kind of problems with it, that it's not really only a search for triangles, but it's a listing of triangles, because remember, we want to find almost all the solutions, almost all the triples. Now, this is one thing, but this can be solved. This can be possibly resolved by just repeating this algorithm the number of times equal to the number of solutions we expect. Now, the second and most important, sort of most annoying problem is that if I look at this literature on quantum algorithms, so quantum triangle finding, it's kind of in the query model. And when I started to analyze this algorithm, not in the query model, but actually in the runtime, because what we need is a runtime, it turns out that it's absolutely not trivial to do this, to kind of set up the correct data structure to implement these quantum walks that are proposed for this algorithms. And those algorithms I've checked, it turned out to be not worth to do this for the algorithms that work in query model. But once I started to actually analyze them with in the runtime model, they turned out to be worse than what than the previous proposals. And the previous proposals, I meant the algorithm of 2001 by Buhrman, De Wolf, Dio, Helling, Hoyer, Magnies, and Santa, which is the paper about element distinctness. And they have one of the sections in the paper dedicated to finding a triangle in a graph of a certain sparsity. And note that our graph is sort of sparse, no, because the probability that the two vertices will be connected is rather small. No, it's not likely that they will be connected. And the way then we just applied the ideas from this paper to our setting, where we estimated the number of edges and the number of vertices from our from what sieving tells us we should have, and we find that that the time to find one triangle, according to this algorithm, is the square root of the number of edges. So the time to list all the triangles, and we actually have to list them all in order to repeat the algorithm, is basically the number of vertices times the number of edges, because the number of triangles we want is equal to the number of vectors, and each vector is a vertex. Okay. There's no question for that so far. So we start computing the runtime, and the runtime for the triple for this triple finding is it turns out to be the 335N for our parameters, which should be opposed to the classical runtime, which is 396. Now, this can be generalized. This can be generalized to k tuples, which will now be not triangles but k cliques. And it turns out that if you go for larger k for large enough k, it actually stabilizes to this runtime, which is 299, and this map. And for now, this is the best quantum, again, by memory, I mean whatever we need to run the quantum triangle finding, and this is a Q run. So basically, we want to query the and the function that tells whether there is an edge or not is simply the inner product. If the inner product is good, it's an edge. If the inner product is not good, it's not an edge. Okay, so I think I should be wrapping up soon, and this is what I'm doing. Now, if you want, so the picture currently is the following. What we have was this sort of triangle and k-clique finding algorithms is the best algorithms when analyzed in time area or times memory regimes, and sort of the best we can do now quantumly is this time and memory that should be contrasted with classical 373 and 168 memory. Still, if we are on the time scale, if we only care about the time scale, the best we can do is k equals 2 and locality sensitive hashing techniques. Now, another thing that we are doing, but in our paper, but I will not be describing here, is what happens if we have full quantum memory. Now, in full quantum memory, we can actually show that there exists a quantum circuit that can implement the 2 sieve of a width, which is equal to the memory, and a much shorter depth. So if you actually want to sort of separate this, these regimes, depth and width, you could also try to do that. Now, to kind of state what we could do next, or what we haven't done, is what happens if we actually have distributed memory or distributed quantum power. We haven't analyzed that neither in classical nor in quantum regimes. I guess it's not absolutely trivial how to do that, but I think this is definitely something to look at. So look at further, and I guess there should be some minutes for questions. I'll be happy to take them.
Okay. Thank you, Elena.
Yeah. No, there's certainly a question.
Yeah, there's a question here I can read. From Danish Furekta. So let me see. He also. Okay, so I'll read the question. So they're guessing if that the sieving algorithm uses the same idea as classical merge sort algorithm, where first you divide the sample space into many parts and then find the smallest. And then they're asking if you can use other similar ideas of classical algorithms, or if to sort this short vector problem.
So, okay, let me try to answer you the first one, if I understood it correctly. That was the question whether I can use this as a sorting. So, sorting really, I mean, we do sort the lists to start. And sorting doesn't cost you much. Sorting costs you soft of the list size. But really sorting is, so it's not really that we're searching for equality. We are really searching for approximate sort of for approximation for the approximate closeness, and really the notion of sorting becomes actually the notion. So you could look at this kind of as a sorting. I mean, this bucketing phase as a sorting. And honestly, I do not know of any other techniques. Maybe I should. I mean, unfortunately, somehow for reasons I cannot. Okay, I see the chat, but I do not see the questions.
But you understand the second question?
Right, and the second question, could you please remind me about it?
If there's other ideas of classical algorithms, or is there any way to sort this problem?
So I guess if there was a way, I would have, I mean, the way we know is this. So this is kind of the state of the art, and if there is another way, possibly, but the best we have so far is really this kind of this algorithm which I've told you. This is really the going through the list twice. Either doing hashing or doing it naively, but this will be worse. So I mean, sorting is really the way we do LSH or LSF. This is the same for me. Okay. I'm not sure if I answered this question, because I mean, really the notion of sorting here is not necessarily what we need.
Mm-hmm. Okay, so Ronald asks, how sure are we that this kind of lattice algorithms are safe against quantum computers? So are there hardness proofs, or is it just it's just been tough to find an efficient algorithm so far.
There is no hardness proof.
There's no hardness proofs. Okay.
We don't have any lower bounds. I mean, the only thing we know is the NP hardness regime, which we are not at. We don't have any lower bounds. I mean, we could state there is no lower bound on this regime SVP. It could be polynomial time. There will be. I don't think there is any contradiction in any hardness where SVP for this regime would be easy. So I think nothing will break down if for gamma polynomial time SVP is I mean, sub-exponential will be definitely nothing surprising. Well, okay, that will be surprising for cryptography people, for complexity theory people. I don't think so. So there is no lower bound. Of course, we could say that if we use this or that technique, like triangle finding, for which we do have lower bounds, or like for classically only LSF or for certain LSH techniques, we also have some lower bound. And the statement we could have, if we use this technique for SVP, we cannot do better than that. But this is, of course, not a proper lower bound because there is an if. We do not know if there is any lower bound on that. I think people try to kind of come up with lower bounds, but I'm not aware of any positive outcomes of that.
Okay, that's funny. Yeah.
I hope this answers the question.
Yes, this answers the question. It's just strange that then people like post-quantum cryptographers are so invested in this kind of methods. If on the other hand, there's no proof that this is indeed hard for.
There is no proof, but it's kind of the. I mean, there is also no lower bound for factoring. There is no lower bound for discrete log problems. It's hard. I mean, crypto is hard because we cannot find better algorithms than what we have.
Yes,
that's it.
Okay, then David Mestel has some questions about in the initial quantum speed up.
Right.
The first one you showed where you only had 2 letters.
I go to that. Yeah.
Why do we do Grovers over L for fixed X and not over L for L? Or also later when you have the buckets, why do you do the Grover like for each X? Search all the buckets and not the other way around. Is there a reason why this is optimal?
So for the optimality, I'm not claiming that this is optimal. Like for this one, yes. I mean, this is the right. This is the algorithm I had in mind when I wrote down this constant. Is that for each X you kind of query the you do the Grover to find a good X, and on expectation you have only one or polynomial many such X. For me, one and polynomial is on this scale is the same. Now, when we go to this buckets algorithm, you could do differently. You could try you could go through the buckets quantumly, but then, as far as I remember, when I tried that, it gave me either the same result or worse. Or worse than the runtime 265. I'm not sure if I can if I can remember my arguments right now. But here is the thing: you would. So what is not so nice about applying quantum algorithms to this regime is that because we use kind of special buckets, quantum algorithms do not help in the following. With the following task. For a given X, find all relevant buckets. Now, classically, this is the same, the runtime for this algorithm when we use a specially structured UIs is equal to the number of these UIs, which is optimal. Now, quantumly, you cannot do better than the output size because we need to actually have them. And so this is why I actually said, phrase the quantum algorithms in this way, because for a given X, finding all relevant U's is as easy classically as easy quantumly because the runtime is already optimal classically. It's the output size.
Okay, so then thank you again. I think this is all the questions for now. So, and Tony, if you can. So if Elena can stop sharing the screen, perfect, yes. And Tony, if you can share a screen.
Thank
Yeah, very good. Maybe full screen, and we would like to see you too. Hi, Tony. Okay, so the next speaker is Tony Metger from ETH Zurich, and he'll present us today the first half of his master's project, which is on self-testing under computational assumptions.
All right, yeah, thanks for the introduction. Also, thanks to the organizers. So this is joint work with Tomamichel Vidick from Caltech. And before I give you a proper introduction, let me give you some sense of where we're going here. So my main goal is to present a protocol for self-testing. And what that means is to certify states and measurements in some untrusted quantum device. Now, there's been a lot of work on self-testing over the years, but almost all of that is in the setting where this untrusted device is sort of split into two parts that are spatially separated and can't communicate with each other. So what's different in our work is that we consider just a single quantum device without any substructure and without any splitting. But instead, we do need to make a computational assumption. And in particular, we assume that the device cannot break post-quantum crypto. Okay, so this is where we're going. But let me start by recapping the basic ideas of black box protocols. So the setting that we consider here is the following. We have some verifier down here, and let's just assume that's you. So you're an entirely classical entity. You don't have any quantum capabilities, but you're given access to this black box quantum device. And the way that you can access this device is that you can send a classical message to the device, and you can receive a classical reply back. But what you can't do is kind of go and open up this device and look inside to see what's going on. So one example that you could have in mind here is that of those IBM quantum computers, which you can access via their cloud interface, but typically you can't actually go to IBM and check that their quantum computer is doing what they claim it's doing. So the manufacturer of this black box device will have told you what is meant to be going on inside the device, right? So they might have told you, well, you can send a quantum circuit to the device will execute it and send back the measurement results. And we call this the desired functionality. But now you might start to wonder whether the manufacturer of this device was actually truthful when they told you what's going on inside, or whether perhaps this manufacturer is malicious and the device is not doing something that's beneficial for you, but maybe rather beneficial for the manufacturer. So this is where device-independent protocols come in. And the goal of a device-independent protocol is to remove any need for trust in the manufacturer. So more specifically, what a device-independent protocol allows you to do is that from purely classical interaction with this black box device, you as the verifier obtain some desired output as before. So these might be random numbers or the answer to some computational problem. But you can also certify that the device behaved as intended. And what's really important here is that this certificate is something that you yourself get entirely from your own observed classical interaction, right? So it doesn't require any trust in the manufacturer. It doesn't require any trust in any sort of third-party certificate. And it doesn't require any assumption about what's going on inside the device. Okay, so that's the general goal of device independence. And now you might say that looks like quite an ambitious goal because, you know, it's just you, a black box. How can you possibly say anything about what's going on inside? And indeed, we do need to make some sort of assumption, some minimal assumption about this black box device. And the standard assumption that is made is that this black box device is really composed of two sub-devices, if you like. And these two sub-devices are spatially separated, and they may be entangled with each other, but crucially, they can't communicate, at least during the protocol execution. Okay? So you as the verifier, you still get to classically interact with each part of this device, but the two devices or two sub-devices just can't talk to each other. So as an example of a protocol in this setting, let's look at standard self-testing. So Henry briefly talked about this yesterday, and what I'll call self-testing is what he called rigidity of non-local games. So this is phrased as a game, and it starts by you as the verifier sampling two random bits, x and y, and you send x to one part of the device and y to the other part. and then you receive back 2 bits A and B, and you have some winning condition that you evaluate, so just some function that takes X, Y, A, and B as input, and outputs either win or lose for the device. And this winning condition is something that's publicly known beforehand. So this device knows what the winning condition will be, and it can adapt its behavior to win with as high a probability as possible. And also remember that these are really sub-devices of the same device. So you should think of them as cooperating in this game. They try to win together, not against each other or something. Okay, so what's the desired functionality here? So what is it that you would like the device to do? Now I'll only talk about self-testing of EPR pairs here. You would like the device to start out sharing an EPR pair across its 2 parts. And you would like your input bit to be interpreted as a measurement basis. So for example, 0 might denote the computational basis and 1 the Hadamard basis. And then these A's and B's that you receive back are meant to be the measurement results of measuring this EPR pair in this requested basis. And now what a self-testing statement says essentially is that if the device wins with sufficiently high probability, then it indeed must have used this strategy. So this strategy is the unique one that achieves the optimum winning probability. Okay? So a bit more precisely, a self-testing statement says that if the device wins with optimum or at least close to optimum probability, and in practice you'd repeat the protocol a bunch of times to estimate this probability, then the state shared by the 2 parts of the device must have been an EPR pair, and each part must have measured its qubit in the basis requested by the verifier. Okay. So this really gives the verifier very tight control of the device's state and measurements. But this statement is actually a bit too strong because each part of the device, so let's look at this right part here, it has some local Hilbert space and it might change the basis on that Hilbert space. In other words, it could apply some unitary or some isometry to all its states and all its measurements on that Hilbert space. And that wouldn't change the classical measurement outcomes that you get to see. So you can't possibly detect this. So you always have to allow for this freedom of local changes of basis. And a good intuition here, I think, is that if we say a state is an EPR pair up to a local change of basis, what that means operationally is that we could have extracted an EPR pair from this state using only local operations. Okay, so this is the definition of standard self-testing, but now let me return to this non-communication assumption more generally. So this originally arose in the work of Bell on non-locality, and of course if you want to study non-locality, it's kind of very natural to have 2 spatially separated sub-devices. But if you're just interested in certifying some black box device, which for example may be sitting on your desk, but you just can't or don't want to open it, then it might be quite unnatural to have to split this device into these 2 non-communicating parts. So this is why the setting that we consider in our work is that of just a single device without any substructure. But now we assume that this device is computationally bounded. So I'll indicate this by these little gears because gears are very slow. So in particular, we assume that the device is unable to break post-quantum crypto and more specifically the learning with errors assumption. So if you watched, I won't say anything about the crypto primitives, but if you watched Venkata's talk yesterday, then essentially we're using what he called the strong TCFs. Okay, so that's the precise primitive that we're using. And the other change that we need to make is that now we have multi-round interaction, whereas this was just a single round interaction. Okay, so the first step that we need to take is that we need to define what we mean by self-testing in this single device setting. So for reference, I've copied the standard definition here on the left. And let's just ignore this multi-round aspect for now and just assume that we send both questions X and Y simultaneously to the device and then receive the 2 answers A and B back and decide on winning or losing. Okay, so let's just translate this definition, and we can start the same way. If the device wins with optimum probability, then the state shared by the device, prepared by the device, must have been an EPR pair, and the device must have measured each qubit in the basis requested by the verifier. So this really is just a one-to-one translation. But now here we talk about local changes of basis, whereas in this setting, we just have a single device, so we can't even define locality in any useful way, right? So now we have to allow for global changes of basis on the device's state space. But now we need to make sure that this global change of basis freedom isn't too much freedom, so that the certificate is still meaningful. And the reason you might get worried about this global change of basis is that if you just look at the state part of the certificate, then saying that a state is an EPR pair up to a global change of basis, which is just a global unitary, that's a meaningless statement because we could map any state to an EPR pair by a global unitary, right? But the point here is that we simultaneously certify the state and the measurements. So in other words, what we're really certifying is how the measurements act on the state, or the relation between the state and measurements. And this relation between states and measurements remains invariant even under global changes of basis. So if we certify states and measurements at the same time, then allowing global changes of basis is actually fine. All right, so now that we know how to define self-testing in this setting, let me briefly mention some previous work. So the setting isn't something that we introduced. It was introduced by Rakursky and others for randomness certification, and by Mahadeb in her well-known verification protocol for quantum computations. And since we've just seen the self-testing definition, just as a brief aside, let me mention the difference between verification and self-testing. So in verification, what you end up showing, or what the verifier can be sure of at the end of the protocol, is that for some local Hamiltonian chosen by the verifier, there must exist a low energy eigenstate of this Hamiltonian. So in particular, you could indeed pick the EPR Hamiltonian, whose low energy eigenstate is the EPR state. But then you end up certifying this trivial statement that the EPR Hamiltonian has a small eigenvalue, which we all knew, right? We all know that EPR pairs exist mathematically. So what we're after in self-testing is the stronger certificate that the device has actually prepared this low energy eigenstate, this EPR pair, and then measured it, right? So that's just the difference between self-testing and verification. Okay, so the last piece of previous work that I want to mention is the remote state preparation protocol by Georgi and Vidick. And using our definition of single device self-testing, we can kind of reinterpret this as single qubit self-testing. So we'll use this single qubit self-testing as a sort of building block for our protocol for self-testing EPR pairs. So let's look at how this works very briefly. In this protocol, we start by fixing some collection of single qubit states. So for concreteness, let's just pick 0, 1, plus and minus. They can do 6 more states, but we don't really need them. And the protocol starts with some setup rounds, if you like, that involve some clever use of post-quantum crypto that I don't want to get into. And at this point in the protocol here, the device, if it behaved honestly, so if it behaved as intended, would have prepared one of these 4 states. So then the verifier sends a measurement basis, just a single one because it's a single qubit state, to the device. The device is meant to measure this prepared qubit in the spaces and send back the result. Okay. And now what is the guarantee achieved by this protocol? The guarantee is that if the device succeeds, indeed, it must have prepared one of these 4 states psi I and measured it in the requested basis, again, up to some global change of basis condition. Okay, so now you can hopefully see why I said this is kind of like single qubit self-testing. Now, one other property that will be quite useful when we try to turn this into our self-testing protocol for EPR pairs is the following. So the verifier knows which state psi I the device has prepared, so which one of these 4. But the device itself does not actually know which state it has prepared. So this might be a bit counterintuitive, but essentially as a result of the use of crypto here, this state preparation is blind in the sense that the device can prepare the state correctly, but it doesn't actually know which state it has prepared. Okay. So we'll use this when we turn this into a self-testing protocol for EPR pairs. All right, so let's turn to our self-testing protocol, and I'll try to give you some intuition here based on this RSP protocol, but the actual proof goes quite differently. So we don't use the RSP protocol in this black box way that I'll use it here for intuition, but I hope this helps a bit. So we're interested in self-testing an EPR pair, so a 2-qubit state. So let's just start with 2 copies of this RSP protocol executed on 2 devices. So then we know that each device should have prepared one of these 4 single-qubit states. And now the next step that we make is we merge these 2 devices into one. So we have one big device, and we just execute our 2 copies of RSP in parallel on this one big device. And now what we need to show, and this is kind of the technically challenging part here, is that this device must still treat each copy of RSP independently, so that it ends up with one register with the prepared qubit from the first copy of RSP and a second register with the prepared qubit from the second copy of RSP. So if you're from CS, this is kind of like a direct product type statement. So on a technical level, just as an aside, how you show this is you define sort of local observables for each copy of the RSP protocol, and then you show that they approximately commute. And that, together with the crypto assumptions, allows you to kind of pull apart the device's Hilbert space into these 2 factors. Okay, so let me rewrite these 4x4 states and sort of classify them into 4 types. So the way you should read this is, this means computational basis state, computational basis state, computational Hadamard, and so on. So now what's left to do is that we need the device to perform some entangling operation, right? Because right now we just have 2 qubit product states, which is not what we want. We want an EPR pair or a Bell pair. So let's just ask our device to perform a CNOT gate on these 2 prepared qubits. But of course, we need to verify that the device has actually done this CNOT, because it's just some black box device. It can do whatever. So how can we certify this? Well, let's just consider what happened if we would apply the CNOT honestly on these types of states. So you can easily check that if you apply a CNOT on these first 3 types of states, then you get back the same type of state. For example, 1, 0 would be mapped to 1, 1, which sure is a different state, but it's the same type of state in our little classification here. On the other hand, these 4 states down here would be mapped to the 4 Bell pairs, so to the 4 sort of maximally entangled states that we're considering. Okay. So why is this a useful observation? Well, it's useful because the CNOT in these first 3 cases essentially has no effect up to relabeling some of the states. And this means that we can take our guarantee that we had for 2 copies of the RSP protocol without the application of the CNOT gate and still apply them here, taking care of this relabeling. But you know, that's doable. So this means that in these first 3 cases, we can still certify single qubit measurements. Now, in this last case down here, we can certify that the device's answers have these Bell-like correlations. So in other words, that the parities of the bits reported back by the device are what we would expect. Okay, so now we need to make one last step, and this relies on this blindness property that I mentioned. So recall that blindness means that in the RSP protocol, the device doesn't know which single qubit state it has prepared, whereas the verifier does know. So in particular, the device doesn't know whether it's in one of these first 3 kinds of product cases or in this last Bell type of case. And that means that the device can't adapt its behavior based on which case it is in. And for us, that means that we can carry over this single qubit measurement certification from these first 3 kinds of cases down to the last one. And in total, that gives us a certificate that we have measured single qubit or made single qubit measurements on the Bell state. And that's the self-testing statement that we were after. Okay, so I hope this gives some intuition for the protocol and why it at least might be secure. So let me summarize. Our main result is a self-testing protocol that doesn't use this non-communication assumption that I mentioned. Alternatively, we assume that the device cannot break post-quantum cryptography, and in particular LWE. And the main technique that this allows us to use is this tight cryptographic leash for black box quantum devices introduced by Berkowski and others at Mahadov. So in terms of future work, I think two questions that are very interesting is, one, can you extend this to arbitrary states? So in the non-communication setting, it's known that you can self-test any pure state. Can you do the same here? And sort of more broadly, are there other interesting applications of this cryptographic leash? So one thing that we're currently working on is doing a QKD protocol based on this single device self-testing that I told you about. But I think there are potentially many other applications of this, maybe also functionalities that just don't make any sense in the non-communication assumption. All right, so I'll stop here. Thank you very much.
Okay, thank you, Tony. Are there questions in the Slack? Let me just check. So I have a very naive question, which is, what happens if you just directly replace the C0 with an arbitrary unitary that you want the prover to implement? Is it possible to certify this as well, or not?
Okay, so the reason why the C0 is special in this case is that the C0 acts essentially trivially on these first three kinds of states. And we need this trivial action to be able to still use our certification from the 2 copies of RSP up here. But if you just applied any arbitrary unitary, then it wouldn't have this property. You would just start with these 4 types of states and get sort of any 4 types of states that don't necessarily still have this nice product property. Mm-hmm. So that's why the C0 is kind of special compared to other unitaries.
Yes. So that it looks like it's very fine-tuned for this specific test. So how do you go about trying to generalize this to, like your first example of the IBM quantum computer that you want to perform an arbitrary computation or circuit?
Okay, well, so the real answer is I don't know. If you just want to verify the quantum computation, you can use Mahadev's protocol, right? Then you don't need the stronger self-testing certificate. You're fine with just showing that there exists this low-energy eigenstate. But extending this or strengthening Mahadev's protocol to showing that the state is actually prepared, I don't quite know what to do, because indeed this is like sort of quite deep that it works out, and it doesn't work out for general gates. So yeah, I don't really know.
Okay, so if there's no more questions, we thank Tony again. And I'd like just to remind everyone that you can continue the discussions on the Slack channel. So I'd ask Tony and Elena to go through the Slack channels of their talks in case there's further questions. And now we have a coffee break, so I hope you enjoy your morning second coffee. And we'll continue at 45 past the hour. Okay. Goodbye.
Hey, can you see me?
Hello, yes.
Hi. Let me know when we can start.
Okay, I am ready. Let me share my screen. PowerPoint share. Okay. I'm ready.
Okay, hello everybody. Welcome to the next session on day 3 of TQC 2020. The first talk is actually going to be a merged talk comprising of 2 presentations. So we first have Farzad Kianvash, who will tell us about quantum flags and the quantum capacity of the depolarizing channel.
Shall I start?
Yes, please.
Okay. So thank you for the invitation. In fact, accepting my talk and also the introduction. This is the work that I did with Marco Fanizza and Vittorio Giovannetti. We are all from Scuola Normale Superiore di Pisa. Here is the logo, and Vittorio is our supervisor, and Marco, probably you have seen his talk yesterday. This is the outline. As our friend told us, this is a joint talk, so it takes like 15 minutes. So it's better if I start faster. Here is the problem and some motivations. This is what we define as flag depolarizing channel. You see here there are 2 terms that are like depolarizing channel with some flags, with something more that we call them flags. There are these 2, sigma 0 and sigma 1, are quantum states that we call them flags. Let me give you some motivations for why we defined the channel in this way. First, this channel is something between depolarizing channel and erasure channel. If we choose sigma 0 and sigma 1 to be orthogonal, it's depolarizing, it's erasure, of course, and if we choose them to be equal, it is depolarizing. So it's something between depolarizing and erasure. So it can be nice studying it. There is also another more practical, let's say, motivation. If we see the problem in the context of communication. In communication scenarios, Alice always wants to send up something. In this case, the quantum state rho. There is environment always, which interacts with the state, and what Bob receives is not exactly rho. It's something different. In the standard approach to quantum communication, we know sigma, we know the interaction, so we know exactly what it is. But let's a bit change the scenario. We assume that, okay, maybe the environment is changing a bit. We don't know exactly what it is. We assume that we only know that with some probability pi, the state is in sigma. And of course, what Bob receives is a convex combination of different states. It's still a channel, but let's give Bob some more information. So we say that if the channel acts as lambda sigma I, Bob looks at the environment, he gets a copy of the state of the environment to compensate for the lack of information that here we have. It can be a toy model for the cases where the environment is changing fast. We don't have a complete description of the environment, so it can be nice also. Maybe the last motivation, and this is the result of our paper too, is that knowing the quantum capacity of flag depolarizing, we can upper bound the quantum capacity of depolarizing, because just tracing out the flags, we get depolarizing channel. And the quantum capacity of depolarizing is important because knowing that you can lower bound this time the quantum capacity of any other channel. This is why people studied depolarizing channel in the context of communication for many years, but still the quantum capacity is unknown. Some background, we know that any quantum channel is a CPTP map. Then you can represent the CPTP map. In this tiny spring representation, there is the system environment interaction with you. If you trace out the environment, you get the channel, but also you can trace out the channel, the system, and what you get is, of course, something that depends on the input state, and we call them the complementary map. So there is this definition which is important. If we call a map degradable, if there is another quantum channel W that maps lambda to the complementary channel. Degradable maps are important in the context of communication. We will see it later. A fast recap of what quantum capacity is. Alice wants to send Bob some information, some quantum state raw. She encodes the state to the big state raw and uses n uses of the channel to communicate with Bob. Bob decodes, and this time Bob gets almost m copies of the original state. The ratio between m and n is the quantum capacity. Of course, we should look at the large limit of n, and we should also, we know that this is almost true. So these are the details that maybe not really relevant for the moment, but the important thing is that Devetek showed that the quantum capacity can be calculated using this limit, where Qn is a maximization problem. Finding Qn is a maximization problem. That for large n, you should find the maximum of this quantity, and as rho n lives in the input of lambda n, the maximization problem is so huge that we cannot do it. But there's a good thing that for degradable channel, Q1 is equal to Q is equal to Q1. So this maximization is not on a huge Hilbert space, is like it depends on the dimension of the input, but let's say T, which can be done. So two more couple of things. This is the diamond norm. Diamond norm of a operator is defined in this way. You extend f and with the identity, then you compute the norm of f tensor I under any pure state. Then having the norm, you can define the distance. The distance between f1 and f2 is the norm of the diamond norm of their difference. And there is this thing that maybe first Long and Smith showed that if lambda 1 and lambda 2, they are two quantum channels, if they are close, then their quantum capacities are also close. This is what I expressed here. The expression for f is known, but I didn't put the explicit expression because it's not important maybe for the moment, but the important thing is that f at 0 is continuous and f of 0 is 0. So it means that if two channels are close, their capacities are also close. Okay, so here I talk about the previous upper bounds, how people found it. One of maybe the first upper bounds, they came from these works of Smith and Smalling, they extended the polarizing channel in this way, where 0 and I are orthogonal flags, and xi are Pauli operators. So they showed that, okay, so you see that if still we trace out on the second subsystem, we get depolarizing. So it's an extension of depolarizing channel. And they showed that for some P, this is a degradable channel, so they found the quantum capacity. There is another way to upper bound the quantum capacity of depolarizing, which is approximate degradability, which is numerical. Suter and his colleague defined this notion of approximate degradability or degradability parameter, which says that, okay, maybe a channel is not degradable, but we can understand how close it is to degradable channels. And this eta defines that parameter. Finding eta for a channel is an STP problem. So you can do it efficiently, and knowing that you, again, using the continuity of the quantum capacity, you can upper bound quantum capacity. So what we did is not numerical, is analytical, and maybe it is close to what Smith and Smalling did. But there is a difference. We add flags which are a bit different from how Smith and Smalling did. And there is another difference which is more important, is that the flags are not orthogonal. You see, the flags are classical. They are both diagonalized in 0 and 1 basis, but the important thing is that they are not orthogonal. And by finding explicitly the grading map, we showed that, okay, for this regime of parameters, this channel flag depolarizing is degradable. And we computed the Q1 of depolarizing, well, flagged depolarizing, which is equal to Q, and put an upper bound on the quantum capacity of depolarizing. Again, our results are analytical, and they work for any dimension of the input state. So let's compare our results with the previous results. Here you see the red line, and also this black line. Is these two are our contributions, and you see that here for d equal to 4, there is a gap between our upper bounds and the previous upper bounds. These two are previous upper bounds. This is our upper bound. In fact, also this black line. And this is the Q1 of the depolarizing channel, which is the lower bound. So it means that, okay, this region here between the red and the solid black line is the value of the quantum capacity lives here of the polarizing channel. Here also we computed it for d equal to 10. We compared our results with the previous results, and still you see that there is a gap here between our results and the previous results. We also compared our results with the numerical results that only exist for d equal to 2. For example, this red line is again our result. This yellow dashed one is from Leditsky, and you see, at least until here, there is a difference, but then the results, they are almost equal. And for really small p, the Sauter, the paper that I already talked about, the blue line, and they do a bit better than us, but after a while, our results get better. In fact, the upper bound, which is lower, is a better upper bound because it's tighter. So, as a future work, I'm on time, fortunately. We can use a general form for the flags. We only analyze the classical flags. We can have a more general flags. We can also choose a different way, a more general way to add flags. We can add flags to the cross operators, as Smith and Smolin did. Or you can also just study other channels using these techniques. So this is, in fact, some of these stuff are done by our friend Xin, and he will talk about it after me. So I'm done. Questions?
Thank you, Farzad, for a very nice talk. I think I already see one question from Ali Musawir. He wants to know what was the dashed line on slide 13 that was almost on top of your new results.
So I didn't explain this, but this is in fact our results, this dashed line, and this black one. And there is this theorem that if you have two bounds coming from degradable extension of a quantum channel, of course for depolarizing channel, their convex combination is also, the convex hull is also another upper bound. So in fact, this black line is our bound, and this is the convex hull of all other bounds. And as our bound is better, the convex hull gets better too.
Nice. There's a question from Maris Ozols. Have you considered choosing the flags to be pure states with a small angle?
So this is what Xin will talk about.
Okay. Maybe we have time for one more question, if there are any. Okay, if not, let's thank Farzad again for a very nice talk. And we can move on to the next speaker, Xin Wang. Just a reminder that any questions can also be asked on the Slack channel, which will be answered offline by the speaker. Is Xin ready? So our next speaker will be Xin Wang, who will talk about optimizing the fundamental limits of quantum and private communication. Hello, Xin, are you ready?
Can you hear me?
Yes, we can. If you're ready, you can start.
Okay.
I'm sorry, but your audio is breaking up a little bit.
Okay.
Hello. I guess Xin is trying to reconnect. Hello, Xin. Yeah, we can sort of hear you off and on, but your connection is breaking up very badly. Okay, let's wait a minute to see if Xin can reconnect. Okay, we're just trying to see if Xin can reconnect by dialing in or something.
Can you hear me?
Hey, yes, we can.
Okay, so I will start. Sorry for the technical issue.
Great, no worries. Please start.
Okay. So
Hello. We seem to have lost the connection again. Xin, could you try dialing in via a phone?
Okay.
Hello, Xin. Okay, there's a suggestion from the organizers that maybe you could record your presentation and post it on the Slack channel. Okay, so maybe Xin will, record and post his talk on the Slack channel. There's a dedicated Slack channel for his presentation. I urge everyone to go look at the talk there later. We move on to the next speaker now, Kamil Korzekwa. Are you ready?
Yes, I'm ready. Can you see me? Can you hear me well?
Sure.
Perfect.
Yeah. Great. So Kamil will tell us about encoding classical information into quantum resources.
I need to share the screen still. Okay. Okay. Can you see the screen?
Yes.
Perfect. Okay. Thank you very much. It's a great pleasure and honor to be giving a talk today at the TQC 2020. And today I would like to tell you about our work to connect the resource theoretic framework with more operational quantum communication scenarios, maybe not even quantum communication scenarios. So this is joint work with, Zbigniew Puchała from Gliwice, Marco Tomamichel from then UTS Sydney, now in Singapore, and Karol Życzkowski from Jagiellonian University in Krakow. So let me start with the outline of my talk. I will first spend a few minutes to tell you about the motivation, which will be based on a communication scenario, a modified communication scenario. And then I will go straight to the results. I will tell you about optimal encodings into resources. And then I will go to applications. So after stating technical results, I will get to tell you about how we can apply it to get some nice results in encoding information, purity, coherence, entanglement, and to look at the bounds for private communication with shared reference frames, and also thermodynamically free encodings and the Zillard engine scenario. Oh, there's a missing quite there. And then I will get to the outlook. If there is any time left, but I'm pretty sure there won't be, I can also give a sketch of some of the proofs. Okay, so I know that most of you probably will know this, but let me start by reminding everyone the traditional communication scenario where we have Alice, and her task is to encode. She wants to send some set of M messages, one of M messages. So she's encoding into a quantum state, a given message M into a quantum state rho M, and then she sends it via a noisy channel, so it undergoes some CPTP map, completely positive trace preserving map, and then the other side of the channel there is Bob, and his task is to decode the message, which basically means perform a POVM, a positive operator value measurement, and trying to guess what the original state was. So getting the N acting on rho M, he has to try to guess what the M is. Okay, this is the standard communication scenario, quantum communication scenario, and we use quantum systems, but we want to send the classical information. And our view on this is that actually in this kind of traditional scenario, we consider Alice to be all powerful, meaning that she can prepare any state she wants. So she doesn't have any constraints on preparing those states rho M. And Bob is also, the receiver is also all powerful in that he can he can choose any POVM he wants. So there is no control over the channel. In the traditional communication scenario, what we deal with is there is some noise, and then on both sides, in Alice's lab and in Bob's lab, they have perfect devices. They can do whatever they want. And we're thinking about modifying this scenario a little bit. And we thought about this constrained communication scenario when you have Alice, and she also wants to send some message M, one of the set of capital M messages. But what she's given a quantum state in a state row, and you can think of this as an information carrier, like a floppy, like an empty floppy disk or a CD-ROM or a CD. What she can do is she cannot prepare any state. She's given this particular state row, and then she's allowed to apply some channels to it, so process it. And those channels EM are constrained, and I will tell you what kind of constraints you consider. But basically, what's going on is Alice has a given state, and then she can perform some CPTP maps on it, and this way encode information. And then we assume that there is no noise. This is the first steps towards this kind of modified scenario. So maybe we will consider noise later, but for now we just assume that they have a perfect communication channel. And on the other side, Bob is as he was before, so he can perform any POVM he wants. So this scenario now is a little bit different. So a receiver is all powerful. This hasn't changed. We have perfect control over the channel. I mean, there's no noise. So this is like a simplifying assumption here. So we simplify it on the noise part, but we generalize it on the sender part, because now we say sender cannot, she cannot do anything she wants. She can only prepare states of the form a channel EM acting on her information carrier row, and those EMs will be restricted. And the question is, what kind of restrictions do we consider? So let me first explain this mathematically. So mathematically, we'll only look at encodings, EMs, that satisfy these two equations for some fixed idempotent channel. So basically, there is some channel D, this is idempotent channel, and EMs are such that if we act afterwards or beforehand of this idempotent channel D, then it's the same as the idempotent channel. An example of such idempotent channel can be a G3 link map, which is just an average over some representations of unitary group. And okay, so this much for maps. And what do we mean physically by this? So we have a system in a state row, and it has some degrees of freedom. There's the whole state space. And then there is some resource destroying map. So there is a map that erases some information. It can be, let's say, decohering map or depolarizing map. Or it just removes part of the degrees of freedom of the information encoded in the state. And now those encodings that we allow are exactly those encodings. They only affect those degrees of freedom that we erase. So so an example is dephasing map, which is basically killing. So this is a map that, if you apply it twice, it's idempotent, because if you erase all, there is some fixed basis I, and this channel acts such that it destroys all of diagonal terms in this basis. So it dephases it completely and gives us a diagonal state. And encodings that would satisfy this encodings that would satisfy those two equations here for the dephasing map would be exactly those channels that only encode information in the coherences, in those off-diagonal parts of the density matrix. Okay, so now that we know what mathematically the constraints are and what the scenario is and what it physically means, again, it's this information carrier. So basically consider those encodings that will encode only in parts of the degrees of freedom of a given state. So in the resources, we say, because the resource destroying map we are thinking about. Okay, so let's get to the results. And to get to the results, the first slide will be to tell you what the main quantities of interest will be. So first, there is the average probability of decoding error. That's basically, as the name says, it's like what's the probability that Bob will make a mistake when decoding the message that he gets. And then there is this MD of rho E, which is the optimal number of messages that we can encode in this information carrier row using those encodings that are constrained by D, so that the average decoding error, as defined above, is smaller than epsilon. And then there is the asymptotic result as well. The asymptotic quantity is the optimal encoding rate into multiple copies of raw. So that's basically the number of nuts or bits per one copy of raw that we can send using those encodings. And okay, so the results. The first result one is a general single-shot upper bound, which is that the number of these messages that we can encode in raw, so that the decoding error is smaller than epsilon, is upper bounded by the exponentiated hypothesis testing relative entropy between a state that we encode into and a state with the removed resource or erased resource. So the hypothesis testing relative entropy between a state and a state with a removed resource is upper bounding the amount of information that we can send, that we can encode in this resource. And then there is the second single shot result, which is the both lower and upper bound for a particular kind of idempotent maps, so those resource destroying maps that are G3 link maps, the ones that I presented before. So those are the maps that are averages over the unitary representations of some group G. And these ones are, those lower and upper bounds are expressed using the information spectrum relative entropy, which is a single shot relative entropies. But what is more important, we use actually this result to get our result 3, which is the optimal asymptotic encoding rate for G3 link maps. So basically those lower and upper bounds coincide up to the second order in the asymptotic expansion. So what we get is that the amount of, for those G3 link maps, we get that the amount of information that can be encoded in the, we can say, asymmetric degrees of freedom, where the symmetric states are defined by those G3 link maps, is given by the standard relative entropy between a state and a state with the removed resource, so G3 state. And then there is also the correction term, which is given by the relative entropy variance between the state and its dephased G3 version. And that's correction goes like 1 over square root of n, that's standard. The other terms are of the order log n over n. And this phi to -1 epsilon is just the inverse of the cumulative distribution, the function of normal distribution. So you can think that this, if we want the error to be small, this term will be negative here, as you can see on the graph on the bottom right. So that basically, if we don't have infinitely many copies, if we have a finite number of copies and we want to have a small error, then we will have to decode the amount of information that we can encode. It will be smaller than the relative entropy by exactly this kind of factor with the relative entropy variance. All right, so those are the mathematical results, the 3 results that we have, and now let's try to think of how we can apply them and what kind of results can we get. So the first and simple thing is, let us choose the group G for this G3 link map to be all unitaries. So then the G3 link map will be just a map that maps every single state to a maximally mixed state. You can think about this as a purity destroying map. So whatever, whatever far your state was from a maximally mixed state, this G3 link maps will send it to a maximally mixed state, and you will destroy all the purity in the states. And then if we look at those 2 conditions that for our allowed encodings, we'll find out that all the encodings that are allowed are all unital maps, so the ones that preserve the maximally mixed state. And then we can get the optimal encoding rate. So what's the situation? So this situation is when you have Alice and Bob, as in our communication scenario, but Alice is only restricted to unital maps. So in a sense, she cannot dump entropy. And then how much information can she send to Bob when she's given a state raw? Well, she has this rate, which is given by log d minus s of raw, where s of raw is the von Neumann entropy. So basically, if she gets a pure state, she can set log d, and then as expected, the bigger the entropy of the state that she has, the less information she can send. And then the second order correction is given by the entropy variance. Okay, so that's a simple first application of this bounds, and then we can get to something more interesting. We can choose a different group. We will just change groups now. So we can choose the group to be all unitaries that are diagonal in a fixed basis. And then the corresponding G-twirl link map is a dephasing map. And the resulting allowed encodings that we get are all those maps that we call population preserving maps. So those are all those maps that in a given basis, they preserve populations or occupations. And you can, again, communication scenario, the same. Alice is given a state raw, but the only thing she cannot change populations in a given basis. Let it be, for example, energy eigenbasis, and she can only control the phase degrees of freedom. So she's trying to encode information in the phases, in the phase degrees of freedom or off-diagonal elements of raw. And then we find that the optimal encoding rate is given by the relative entropy between a state and its dephased version. So this is a nice way. This quantity is also known as, this is the relative entropy of coherence. This appears as a monotone in the resource theory of coherence, and I think this is a nice operational justification of this quantity. There's also the second order rate, which is the relative entropy variance of coherence. So we also know how it kind of approaches the asymptotic value when we have a finite number of systems. And all right, let's go a little further. And now we can choose a different group. And now we can consider a situation when we have a bipartite system, and we choose the group to be all unitaries on the subsystem A of a bipartite subsystem, system A and B. And the corresponding G-twirl link map will be just an entanglement destroying map, which is like, just return a maximally mixed state on the Alice side, and the whatever on the Bob side to just do the partial trace of whatever was at Alice's. And you find out that then the resulting allowed encodings that we have are all local unital channels on A. And the scenario you can get there is basically super dense coding scenario. So you have Alice and Bob sharing some state initially, and Alice can only do something on her side, and she can only locally modify her subsystem, and then she can send it to Bob. So Bob has now the whole state A and B, and he tries to decode what the message was. So this way, basically, we find the second order expansion of how much information can be encoded in a bipartite system raw. So, the standard thing is that in a maximally entangled bell pair, let's say you can encode 4 states, but what if it's a little bit of, let's say it's a little bit mixed state? How does it behave if you put some noise and so on? So here we get exactly the expressions for the rates and how they approach asymptotic values. So those are given with the conditional entropy and conditional entropy variance. Okay, and let's get further. And now we can also think about how trying to applying our results to private communication with shared reference frames. So what's that? So basically, what you have is you encode, information is physical. So you not only are encoding zeros and ones, but you can, let's say, encode in directions. Let's say I'm sending a spin up or spin down, but you have to know along what axis, you have Cartesian frame of reference, and you need to know that, my up is along some axis Z. And so now we have Alice and Bob, who exactly have the X, Y, Z and X prime, Y prime, Z prime Cartesian frames very well aligned. And then there is some eavesdropper, and she does not know the reference frame alignment between Alice and Bob. So basically, if she eavesdrops the message that is being sent, what she's gonna see is a G-twirled version of a state, because she will have to basically average over all possible relations of her reference frame to the Alice's reference frame, and therefore, since she sees only G-twirled version, and our encodings are such that whatever you encode and then you G-twirl, it's like G-twirling, is the amount of information that we can send is exactly private, in the sense that if the eavesdropper intercepts any of those messages, she won't be able to decode it, because all of them will look exactly the same to her. So our rate is also giving you the rate with the private communication with shared reference frames. And finally, let me get to the final application on the thermodynamics. So now we can think of choosing these resource-destroying map. Now we are not using anymore the G3 link maps. We are using a map that sends everything to a thermal equilibrium state, to a Gibbs state, some fixed state that is not a maximally mixed state. And then you find out that the allowed encoding that Alice can do in her lab are all those operations that preserve the thermal equilibrium state. In a sense, this is like the simplest way of trying to encode the second law of thermodynamics, which is, you know, if something is in thermal equilibrium, you cannot move it out of equilibrium. And that's already capturing this kind of constraint, or is already capturing a lot of the second law. And so then we find out that the optimal encoding rate, so now we only have the upper bound, so we cannot say it's equal up to second order. We only have the upper bound, but we actually do believe we are on the track to get to be able to prove that the lower bound is exactly the same up to second order. So what we get here is that the upper bound is given by this relative entropy between a state and a Gibbs state, which is the generalized free energy. So that's, you know, the standard free energy is the average energy minus that background temperature times the entropy of the system. And then there is the correction that goes like, you know, that's a relative entropy variance between a state and its thermal version. And it was shown that it behaves like generalized heat capacity. So you know, we can think of something like the irreversibility of the Szilard engine. Let me just quickly remind that the Szilard engine is taking information and giving you work, so free energy out. And here you take a state and you check the amount of the free energy in the state allows you to, you know, do that kind of a reverse thing. You take a free energy and use it to be able to encode information. And when I say reversibility, because we had this second order correction, which is basically that if you don't have many particles there, you're gonna have a correction term that's gonna behave and depend on the heat capacity of the system. And okay, I think I'm pretty well on time. I think maybe 2 more minutes left, so I will get to the outlook. And so there are a few that direct. Okay, so first of all, at the bottom right, you can take a look at the archive paper, and with all the details if you're interested. And then let's see what's to be done in the future. So one thing is we can, you know, we just choose a few unitary subgroups that came to our head. I mean, those were the most obvious, like take all unitaries or diagonal unitaries or local unitaries. And we were able to find nice, you know, bounds on superdense coding and encoding into coherences. But maybe there is, you know, maybe someone can think of a nicer and operationally relevant subgroups, and also then you just take a result and it's a machine that just gives you the outcome straight away. The other thing is to find single-shot lower bounds for general resource-destroying maps. So we were only dealing with the lower and upper single-shot bounds for those special ones, that the G3 link maps. But it would be very nice to find this, you know, single-shot lower bounds for general resource-destroying maps. So general idempotent CPTP maps. And in particular, what we are doing now and what we would like also to do in the future is to focus on these thermodynamically free encodings, because this seems to be a very interesting path to connect, you know, using resource theory to connect this, on the one hand, the communication games or communication scenarios, and on the other, the second law of thermodynamics, and having this irreversibility of the Szilard engine. And then an obvious step forward also is to try to assume that not only that Alice is not all powerful and she's constrained, but also that there is some noise on the way, because, you know, now it's a little bit of a toy model that the channel between Alice and Bob is a perfect identity channel. And yeah, and maybe the final thing is also, you know, you can look at this resource theory of asymmetry, and then we know that the rate is given by the relative entropy between a state and its dephased version, sorry, the G-trial version. So it would be nice to find, let's say, pure states that are G-trial to a maximally mixed state, because then we would know that this optimal rate would be just log D, and you know, that in this case we can send as much information as it's really possible. And yeah, that's all. Thank you very much.
Thank you, Kamil, for a very nice talk. We have time for a few questions. So I don't see any questions yet. So let me ask a quick question of my own. So correct me if I'm wrong, but I think with any of these unitary groups, you have only considered equal mixture of a set of random unitaries, right?
Yes,
whether
yes. This is actually detailing. So it's a random.
Yeah. So what might one say if one has instead a kind of convex sum of random unitaries or some such, rather than just an equal?
I see. I see. Well, it possibly could be. It possibly could be studied as well. I haven't thought about that, but the most important thing there actually in the derivations, as far as I remember, is that those those mixtures of unitaries are unital. So even if you take a non-equal mixture, non-uniform, then it should. I think that most of the proof should still follow, because the main thing that it was depending on was the fact that they are unital. So yes, exactly. That's something one could take a look at. Thanks a lot.
Yeah, that would be a simple generalization.
Yes, definitely. Thank you for this question.
Are there any other questions? Okay, maybe I can just ask one more. Have you also considered a scenario, this is just, again, just loud thinking on my part, but when you consider diagonal unitaries, unitaries that are diagonal in sort of complementary basis or like mutually unbiased basis, and
yes,
whether that would...
yes. So definitely, this was actually one of the questions the referees of our paper asked was, what can we think of getting some complementary results? So let's say Alice is trying to, so we have some, because what we are claiming is that we are encoding in some resources. So the question would be, are there resources that are complementary, right? So if you, let's say, want to encode in coherences in one basis and then encode in the coherences in the other basis, you could think of a scenario, let's say that Alice is encoding something in her information carrier, sending it to Bob, then Bob encodes something more and sends it to Charlie. And then Charlie's task would be to try to decode both Alice's information and Bob's information. So then definitely there will be kinds of, what we expect is that you would get some trade-offs, like coming from non-commutativity. Let's say if you do two mutually unbiased bases, and so on. So yes, that's definitely something very much on our radar now to look at those complementary resources and basically go with kind of uncertainty relations beyond just observables to resources.
Yeah, so my question was also coming from the uncertainty angle in some sense. Thank you. So if there are no more questions, let's thank Kamil again for a very interesting talk. And I encourage people to also interact with the speaker on the Slack channel. Can we move on to the last speaker of the session now? We have Dina Abdelhadi.
Hello.
Hi.
Can you hear me?
Yeah. Could you share your screen, please?
All right.
Okay, our final speaker for the session will be Dina, who will tell us about second-order asymptotics of quantum data compression and state merging.
Yes, I can share the screen while the other screen is shared.
Kamil, I think you'll have to stop sharing screen and... Could you share screen now, Dina?
Yes, yes. So can you see it now?
Yeah, please go ahead.
So today I'm going to talk about deriving second-order tight bounds for quantum compression using a newly introduced quantity called the partially smooth conditional mean entropy. I worked on this with Renes at ETH. So we're all familiar with the classical task of data compression, where we try to map some classical information into a shorter description, and then we may have to make sure that when we decompress this description, we can recover the original message with high probability. For quantum compression, we try to do something similar, except that instead of compressing classical information, we're trying to compress a quantum state. And this quantum state could possibly be entangled with some other system. So here, for example, Alice holds the system A, and it's probably possibly entangled with a system R. And Alice can only apply operations to her system such that she can compress it into a smaller dimension L. And after decompression, we require that the state that we reconstruct, this rho tilde, has a high overlap with the original state. So the optimal rates and optimal compression lengths for classical and quantum compression have been studied for a long time. For classical compression, the first order rate is the Shannon entropy, and the second order expansion also has been known for a long time. And the meaning of these expansions is if the rate that we are trying to find is the log of the optimal compression length over n. So we're trying to compress n IID copies of that are distributed according to p. And when we have in the limit of n being infinite, we can achieve compression, and with arbitrary like we can let epsilon, or the error probability, go to 0 as long as we compress in a length that's given by the Shannon entropy. And a similar explanation holds for the quantum compression case, where the first order rate is given by the von Neumann entropy. Now, the meaning of this expansion is for the finite case, when n is not infinite, we're trying to find an approximation for the growth of this optimal rate. And you can see that the first order rate doesn't even depend on this error probability that we require. But when n starts becoming finite, this error dependence shows up. And this term could be understood as the expectation, for example, because these results sort of come from a law of large numbers. And the second order rate is sort of like the fluctuations or the standard deviation around the mean. So similarly, for quantum compression, the first order rate is given by the von Neumann entropy, is defined here. And the second order expansion, however, until recently has had this gap that we can see between the upper and lower bounds. And this bound was derived in 2015 by Data and Liditsky, and for the achievability bound, they use this straightforward map to show achievability, where they project the state onto the space of the largest eigenvalues, like the eigenvalues that are bigger than some threshold. So one might ask whether it's the achievability bound that's not tight, so whether we need some more sophisticated achievability map to prove a tighter bound, or whether the converse bound is not tight. And this is the main contribution of our work, where we show a second order tight bound for compression. And we can see that actually the achievability bound is tight. It's the converse that's not tight, which means the straightforward compression map is optimal, at least to the second order. And to derive this second order tight bound for this basic quantum protocol, we needed to use, we needed to derive second order asymptotics for the partially smooth conditional mean entropy, which we will define later, for the pure state case. So here's a plot of the results we get. Like here, the red curve is the original achievability bound from the paper in 2015. And this blue curve shows the new converse that we derive in this paper, and we can see that they quite match here. And these are curves like for the optimal rate of compression as they grow with n. And you can see that the new converse is much closer to the achievability bound than the original converse given in this light blue curve. And this is all derived for the qubit state, like n IID copies of a qubit state given here by these parameters. And this black curve just gives a a related quantity, the hypothesis testing relative entropy. So now let's see how we can derive these bounds. So to derive the results that we have, we go through a few steps. First, we have to relate the quantum compression protocol to the quantum state merging protocol. This is because there are a few bounds known for state merging that are quite tight and have been recently derived. And these bounds are given in terms of a quantity called the partially smooth conditional mean entropy, for which we try to derive an asymptotic expansion that helps us obtain a tight second order bound for quantum compression. So first, let's discuss the task of quantum state merging. In this task, Alice and Bob share a state which is possibly entangled with an external system R. This is a pure state, and the goal of this protocol is that at the end of the protocol, Alice and Bob use their resources to transfer the state from Alice's side to Bob's side. So Alice and Bob are allowed free classical communication, and they have some shared entangled pairs. They use up these resources such that at the end of the protocol, we have a state shared only between Bob and the reference system, and its close in purified distance to the original state rho ABR. So to relate this task with quantum compression, we take a look at a special case of state merging when Bob's state is trivial. So in this protocol, we're just trying to move a state rho AR to a state rho tilde AR shared between Bob and the reference system, and that's close to the original state rho AR. In this case, we can accomplish state merging by a two-step protocol, which consists of a compression step and then a quantum teleportation step. So for this protocol, Alice first compresses her state into a state of dimension L. And after the compression step, Alice and Bob use the resources they have, the entangled pairs and the classical communication, to teleport this state of dimension L to Bob. And then he can decompress and reconstruct a state rho tilde that's close to the original state, and thus achieving state merging. Now we know that Alice's state was of dimension L after compression, which means that the teleportation protocol's cost would use up L entangled pairs from the ones that Alice and Bob have. So the state merging protocol is like the cost of the state merging protocol is exactly how much of the entangled pairs are used up to accomplish state merging. So in our protocol here, we use exactly L entangled pairs to accomplish state merging. So this means that when Bob's state is trivial, state merging is achievable by compression followed by teleportation, which means that the entanglement cost of this state merging protocol is the compression length L. And this means that compression inherits any converse or lower bound on the cost of state merging, because we constructed a protocol that used L entangled pairs. So maybe the optimal state merging cost would be less than that, but it's definitely not more, because we've shown achievability of a state merging protocol of a cost L. And then how does this help us with our original question about quantum compression? Well, first we have to take a look at the existing quantum state merging bounds. Some of these bounds are given in terms of a quantity called the globally smooth conditional mean entropy. And this is the notation we use for it, or that's used in the literature for it. For this quantity, an asymptotic expansion exists. However, the bounds are not tight enough for our purposes. But recently, Anshu, Berta, Jane, and Tomamichel introduced partially smooth information measures, which they used for deriving bounds for several protocols. And for the quantum state merging protocol, they show that the entanglement cost is bounded using this partially smooth conditional mean entropy, denoted here. Unfortunately, an asymptotic expansion for this quantity is not yet known in the general case. But these bounds are tight enough for our purposes. So as a consequence of our previous discussion on the relation between the bounds of compression length and state merging, we get this lower bound on compression length. And now we have successfully related state merging to quantum compression. Now let's take a closer look at this quantity called the partially smooth conditional mean entropy. First, this is the unsmoothed version of conditional mean entropy, and that's the definition for it. If we want to get an intuition for what this means, we can think of the classical case when instead of having a state rho AR, we have, for example, a joint distribution PXY here, and the marginal distribution PY here. Then this would be some quantity in terms of a conditional probability distribution. Now for smoothing, we just replace this fixed state rho AR by a smooth state sigma AR, which is allowed to be subnormalized, but it has to be close in trace distance to the original state rho AR. So this gives us the definition for the globally smooth conditional mean entropy in the pure state case. Now the partially smooth conditional mean entropy, as defined in this paper by in 2018, is the same SDP, is the same definition, except instead of the subnormalization condition, we have a stricter condition on the marginal, where sigma AR must be smaller than rho R and this is the definition of this partially smooth quantity. So we can see we have a semi-definite program here, and as a main contribution of, or one of the main contributions of our work is that we show that for the pure state case, this semi-definite program we showed earlier is reducible to a quadratic program as shown here. And to show this, we can have a look at some of the proof highlights. The first step to reduce this semi-definite program to a quadratic program is that we reduce this bipartite semi-definite programs on two systems A and R to a semi-definite program on one system R. And we can do this by showing that applying some isometries preserves the optimizer of this program. And in the next step, we reduce the single system SDP to an equivalent quadratic program. We do this by first solving this quadratic program, showing that we can construct an optimizer for it. And from this optimizer, we can construct a solution for the single system SDP, which is feasible. So this shows one side of the bound. And to show that this feasible solution is indeed optimal, we use duality. So we have to have the dual SDP program for this. And then we show feasibility and complementary slackness of these constructed optimizers. And most of the steps are straightforward, except to show the feasibility of one of the constructed variables, one might need to use Weil's inequalities, or one of these inequalities. So that's a quick look on how to reduce the SDP to this quadratic program. So since we now have this quadratic program, this allows us to, since it's much simpler as we can see here, this allows us to numerically manipulate it and to derive a second order asymptotic expansion, as we will see here. So if we just take a look at the form of the quadratic program and compare it to the definition of the hypothesis testing relative entropy, we can see they look quite similar, especially that the optimizer of the quadratic program has this form, which reminds us a bit of the optimizer for hypothesis testing. Of course, the details are a bit more involved to show that indeed this quantity is bounded by the hypothesis testing relative entropy, but that's the essence of it. And we're lucky because for the hypothesis testing relative entropy, an asymptotic expansion is known. And since we have this relation between the partially smooth conditional mean entropy and the hypothesis testing relative entropy, as we've explained, for the pure state case, this means that the partially smooth quantity inherits the asymptotic expansion of the hypothesis testing relative entropy in the pure state case. So let's see what we have managed to accomplish so far. We've related quantum compression to state merging. Therefore, the compression inherits the bounds on entanglement cost or lower bounds on entanglement cost. And we know that the entanglement cost is lower bounded by the partially smooth conditional mean entropy. We show a quadratic program reduction of this SDP for this quantity, which allows us to have this relation and an asymptotic expansion for the partially smooth conditional mean entropy. Therefore, we have this asymptotic expansion for compression length. So now it's time to just discuss some final remarks. We see here, this is the asymptotic expansion for the partially smooth quantity as compared to the globally smooth one. For the pure state case, we note that the second order is different. And then an interesting question would be, what is the general asymptotic expansion for the partially smooth quantity? This is an interesting question also because the partially smooth quantity in general gives bounds for other protocols than quantum compression, for example, a state merging. And one might think that this expression for the pure state case would hold for other kinds of states that are not pure. However, if we consider a classical state of this form, which is a mixed state, then we can show that the globally smooth and the partially smooth quantities coincide, which means that in that case, the asymptotic expansion for the partially smooth quantity would have the form of the second equation here and not the first, which means that the asymptotic expansion of the partially smooth conditional mean entropy is not uniform across states. And it might mean that some dependence on the state would show up here in this term, as opposed to like all these other expansions where the dependence on the state is just encapsulated in this variance quantity. So that's all I have to say for today, and thank you very much. And if there are any questions, I would be happy to take them.
Thank you, Dina. We have time for a few questions. So while we wait for questions, maybe I ask a very naive one. I noticed that there is a factor of square root in the second order term that shows up when you go from, I think, state merging to hypothesis testing. Is that correct? Or could you provide some intuition on why this factor of square root shows up?
You mean here?
Yeah, yeah, exactly, yeah. Can one understand why the square root, why it's square root in order 1 minus epsilon?
So the state merging protocol and the compression protocol, like the requirements are defined for the quantum compression protocol, they're defined in this entanglement fidelity. Like we have to require some entanglement fidelity, and the state merging is defined in terms of purified distance.
Okay.
And and then when you write out this semi-definite program, reduce it to a quadratic program, you see that this is the quantity to compare. You have to compare it with the hypothesis testing with a square root.
Okay, so can I understand this as going between entanglement fidelity and the Beer's metric? Is it the same kind of square root factor that shows up typically when?
I'm not sure.
Okay, anyway, I was just trying to see if one can understand that more intuitively. So we have a question from Hayata Yamazaki. Thank you for a nice talk. So I'm just going to read out the question. The entanglement cost of one-shot state merging under one-way classical communication and that under two-way classical communication can be different. Is there a possibility of two-way classical communication affecting the second order rate, or does your analysis cover two-way communication also? Did you get the question?
Yeah, yes, I'm reading it. 1 second.
Sure.
So it's an interesting point to consider. I will have to take a look first, and maybe I'll try to answer it on the Slack channel.
Okay. Any other questions for the speaker? Okay. If there are no more questions, let's thank Dina again for a very interesting talk. And of course, one can always go to the Slack channel for more interactions with the speaker. And that brings an end to the session on quantum information theory. I think we break next for the poster session. And I think there's an hour-long poster session after this. Thank you, everyone, and enjoy the rest of the conference. Thank you.
Okay, it's 18:05 in Latvia time. So I think we are ready to start the next session. And quick reminder, if people haven't, you probably know by now, but you're very welcome to ask questions in the question and answer box down here. And I think there is also the Slack channel as a possibility to ask questions. If you have technical problems, you should use the chat box instead. And so without further ado, I will ask Subhasree to share her screen. Sorry for the delay. Let's see if we can fix this.
Are you able to see me? Yeah. I'm ready. Can I start? Okay. Hi,
I
everyone.
don't hear you. I cannot hear you right now, so.
Are you able to hear me?
Oh, now I can. Now it's perfect.
Okay.
So first speaker of the session is Subhasree Patro from CWI, right, and QSoft, who's going to talk about quantum strong exponential time hypothesis. So please go ahead.
Okay. Hi, everyone. I'm Subhasree Patro, and I'll be talking about the framework of quantum strong exponential time hypothesis. This is a joint work with Professor Harry Buhrman and Florian Speelman. Let's begin. So let's look at the satisfiability problem. What do we know about satisfiability problem? Given a Boolean formula of input with input variables, we want to know if there exists an assignment to these variables that satisfies this formula. Let's look at an example. Here, this is a formula with 3 input variables, and we want to know if there is any assignment that satisfies this formula. So if you look at this particular assignment, the first clause is not satisfied. So the formula is not satisfied because the formula is AND of these 3 clauses. However, if you just change the x3 to 0, all the clauses are satisfied, hence the formula is satisfied as well. Now, when the formula is in this conjunctive normal form, that is, the clauses are connected by and the literals are connected by or, and when the clauses are of arbitrary length, that's the length is not bounded, then we call this as the CNF SAT problem. Okay. Now, what do we know about the CNF SAT problem? We know that it is NP-complete problem. So a polynomial time algorithm for CNF SAT, a polynomial time classical algorithm for CNF SAT is highly unlikely. The best known classical algorithm
runs in 2 power n time. For the purpose of this talk, I'm going to ignore all the polylogarithmic or polynomial factors in speed up, okay? We also know that the best known lower bound currently is n. So as we can see, there's a huge gap between the known lower bound and the known upper bound. So that in 2001, Impagliazzo, Zain and Paturi conjectured that there might not be any faster than 2 power n classical algorithm to solve CNF-SAT on n variables. And they called it the strong exponential time hypothesis, abbreviated as SET. Now, do note that this conjecture assumes a lot more than if we assume P was not equal to NP. That's because P not equal to NP would just imply a super polynomial lower bound for CNF-SAT. But this conjecture says that CNF-SAT needs 2 power n classical amount of time. Now, SET conjecture became instrumental in proving various lower bounds for various problems. To start with, given that CNF-SAT is an NP-complete problem, we can use SET to prove specific exponential lower bounds for many other NP-complete problems. Interestingly, SET also gives exponential time lower bounds for problems outside of class NP. Like, for example, it is shown that conditioned on SET, strong simulation of various quantum computational models take exponential time classically. But what was surprising that in spite of CNF-SAT being a problem in NP, SET implies polynomial lower bound for many problems in P. And one corollary to that would be a SET-based n-squared lower bound for proof of useful work scheme by Ball, Rosen, Sabin, and Vasudevan. And for the purpose of our talk, we are going to focus on these implications of SET, the polynomial lower bounds given by SET. So the first polynomial lower bound that was given by Ryan Williams. He gave an elegant reduction from CNF-SAT to orthogonal vectors problem. What he showed was any subquadratic algorithm for orthogonal vectors would actually give an algorithm for CNF-SAT which would be faster than 2 power n, which means it would render SET false. Now, this orthogonal vectors problem also became a central problem for many other string comparison problems. So there were reductions given from orthogonal vectors to, say, edit distance, fresh edit distance, LCS by Bakkerson-Dyke, Brinkman, and Kuhnman. And what they also showed that any subquadratic algorithm for these string comparison problems would mean that there is a subquadratic algorithm for orthogonal vectors problem, which in turn would render SET false. Now, an interesting part was to see that all these algorithms are, all these bounds are actually tight. So here SET gives a explanation of why people were not able to find, say, subquadratic algorithms for orthogonal vectors or string comparison problems. But SET doesn't hold relative to quantum computation, because we could use Grover search and solve CNF-SAT in 2 power n by 2 time. So all these SET-based lower bounds that we just saw don't directly hold in the quantum setting anymore. But what is interesting to see is the best known classical and the quantum algorithm, they barely use the description of the formula. So the speed up that comes in the quantum case is because of the unstructured search over all the assignments given, over all the assignments to the CNF-SAT formula. So it is natural to conjecture that there might not be any faster than 2 power n by 2 quantum algorithm for solving CNF-SAT. While we call this as a basic QSET conjecture, at around the same time, this was also conjectured by Aronson et al. But let's see how useful this basic QSet is. So let's revisit this overview. And so our basic QSet would mean that we have a 2 power n by 2 lower bound for CNF-SAT problem. And we were able to give a non-trivial reduction, which is very similar to this classical reduction, but it is a quantum reduction. And we were able to show that we were able to give a lower bound of n for the orthogonal vectors problem. Using the same trick again, we were also able to show a linear lower bound for these string comparison problems. Okay. Now, while this basic QSet was interesting to show these bounds for orthogonal vectors and CNF-SAT, because these are tight, it wasn't very interesting for these string comparison problems. That's for two reasons. One, because we can get these linear lower bound for these string comparison problems unconditionally as well. And the second reason being, the best known quantum algorithm for these string comparison problems are quadratic. So there is a gap between the upper bound and the lower bound that the basic QSet is not able to capture. So yeah, so here the basic QSet loses some explanatory power. So that probed us to build the QSet framework. Okay. Yeah. Okay, let's recall the CNF-SAT problem again. Given a CNF formula with n input variables, we want to know if there is an assignment that satisfies this formula. In other words, say we are given the formula, but what we want to know is if there is a 1 in the truth table of the formula. For those of you who don't know what a truth table is a, like say for the formula is on n input variables, then the truth table is a 2 power n bit string, which is just concatenation of the outputs of the formula on every assignment to that formula. Okay. So equivalently, what we are saying when we want to compute CNF-SAT on phi is that we are actually wanting to know the output of this function or on the truth table of the phi. Okay. Now, the best known quantum algorithm for CNF-SAT takes order 2 power n by 2 time. And the quantum query complexity for this Boolean function or on 2-bit long strings, 2-bit strings, the 2 power n bit strings is actually order 2 power n by 2, and that is tight. But what if we are not interested in the satisfiability problem, but we are interested in some other property of the satisfying assignments, say like parity? So given a formula with an input variables again, we want to know if there are odd number of satisfying assignments to this formula. And we call this problem the parity CNF-SAT, and that is equivalent to actually checking the parity of the truth table of that formula. How much time would we need quantumly to solve parity CNF-SAT? Okay. Now, one important thing to note is the quantum query complexity of parity on all the 2 power n bit string is 2 power n. Okay. And also, it appears as if the parity CNF-SAT is not amenable to Grover-like speedups. So again, it feels natural to conjecture that there might not be any 2 power n, any algorithm faster than 2 power n that can solve parity CNF-SAT quantumly. Okay, there is similar conjecture in the classical setting as well. That's also called parity set. Okay. Now, what it appears what it appears is these conjectures, this basic QSet and the parity QSet that I just talked about, indicate that the quantum time complexity of computing CNF-SAT or parity CNF-SAT is lower bounded by the query complexity of these OR and parity functions on the truth table of these formulas. Okay, that is what it looks like. So what you're doing essentially is, given a formula, you're actually trying to compute the query complexity of the truth table of the formula. Okay, but we will see in a short while why. But these Q-set conjectures, the parity and especially the parity conjecture, they indicate something stronger. Here is why. Now recall that the formulas that are of interest to us are these polynomial sized CNF formulas. Okay, so the equivalent set of truth tables of these formulas will be a tiny fraction of all the 2 power n bit strings. Okay, and the query complexity of this OR function on all these 2 power n bit strings is 2 power n by 2. But fortunately, the query complexity for OR on this set of small, on this small set is also 2 power n by 2, because the hard instances of OR can be actually generated by small CNF formulas. But that's not the case with parity. While the query complexity of parity is order 2 power n by 2 on set of all strings, the query complexity of parity on this small set is actually order 2 power n by 2. So in fact, what is surprising is that this holds for any property. When the set is small, the query complexity is not too high. This was the first algorithm was given by Ambinis et al, and later it was improved, further improved by Kothari. But one good news is, good news for us is this algorithm is extremely time inefficient. It is a very good query algorithm, but not at all a good algorithm when we have to see the time complexity. So that kind of led us to, that motivated us to introduce the notion of compression oblivious properties. So how do we define? We say a property is compression oblivious when the time taken to compute this property on a small set of, on a small set, that is a set of truth tables or small formulas, is at least the query complexity of this property on all strings. So like we saw, parity would be something that we would think as compression oblivious, right? Because, first, clearly OR is compression oblivious because the query complexity of OR on the small set of string and on the big set of string is the same. And our basic Q set kind of gives out that the OR is compression oblivious. Now, parity Q set would also imply that parity is compression oblivious. Okay, so it is reasonable for us to believe that parity could be compression oblivious. But what if we want to talk about other properties, not parity alone, not majority, not OR, but some other kind of properties? That motivated us to give the Q-set conjecture. So we give this as a general Q-set conjecture. We say that given a formula, if we want to compute a compressional oblivious property on the truth table of this formula, the time taken would be the query complexity of this property on all strings. That is the conjecture that we give. And clearly, our general Q set would imply the basic Q set. Like using this Q set conjecture, we can say that our basic Q set conjecture that we defined earlier is implied. That is because this conjecture says for all the compression oblivious property, the time taken to compute this property on the truth table is lower bounded by the query complexity of the property. So also kind of suggesting that the description of the formula doesn't or barely helps for these compressional oblivious properties. And as we saw how OR is compression oblivious, our Q-set conjecture just implies basic Q-set. But our Q-set conjecture, along with the assumption that parity is compression oblivious, would imply parity Q-set. So this is what we are at. Okay. Now, the initial applications of Q-set are as follows. We use this Q-set framework to prove a non-trivial n power 1.5 quantum time lower bound for the edit distance problem. So let's recall the edit distance problem. We are given two strings A and B defined over an alphabet set sigma. Now the edit distance is defined as the minimum number of operations required to convert A into B. And by operations, I mean insertions, deletions, and substitutions. Now let's take a tiny example. So we have those two strings, beagle and patches. The edit distance is 4. So one way to convert beagle to badges would be to delete E, insert D, and to delete L and insert S. Okay. Now the idea of our reduction is as follows. So we study the reduction from satisfiability to edit distance by Abad et al. What we noticed is that this reduction just doesn't encode the OR property of satisfying assignment, but it encodes something more complicated. And we name this property as p-edit. But because p-edit is a little more complex and given the time constraint, I'm going to explain another property called OR of majority, which is very similar to p-edit. So I'll give you the flavor of how the property looks. So say you're given an n-bit string and it's divided into root n blocks of root n bits each. What you want to know if there exists a block with majority of ones in it, okay? And the query complexity of this property is n power to 0.75. This is for when the string is of n, capital N bit long, okay? Yeah. Now using the quantum adversary method, we were able to prove a lower bound of the same quantity for our p-edit property. So we were able to prove that the query complexity of p-edit on all the n-bit strings is n power 0.75. Now assuming p-edit is compression oblivious and assuming our Q-set framework, we were able to show that if you are given a formula and if you want to compute p-edit on that formula quantumly, that would take 2 power 0.75 n time, okay? Which again, because of the reduction from satisfiability to edit distance, translates into a quantum time lower bound of n power 1.5 for the edit distance problem, okay? Now, we have assumed that p-edit is compression oblivious, okay? But we think it's a very natural assumption to make, especially when given that it's not really easy to prove if a property is compression oblivious. The OR case was kind of special. So for any property which has strictly, higher query complexity than, strictly higher query complexity than OR, we are able to in fact show that proving P is compression oblivious for those properties would actually separate P from P space. That's how difficult it is to prove compression obliviousness. So again, assuming parity is to be compression oblivious, we are able to translate the set-based classical lower bound that I mentioned earlier for these scheme of proofs of useful work in the quantum setting as well. Now to conclude, the future directions are numerous. We could use the Q-set framework to give conditional lower bounds for additional problems in BQP. The easy target would be the other string problems, but we believe we can use this not just in string comparison problems, but other problems as well. Additionally, the notion of compression oblivious properties are potentially very interesting. We are really curious, like say, for example, we are curious to know the implications of parity being not compression oblivious. We want to know what complexity assumptions it breaks if parity is not compression oblivious. And lastly, there are other core problems in fine-grained complexity like 3-sum and APSP. APSP is like all pair shortest path problems, which were also used like CNF-SAT to prove lower bounds in complexity class P. So we could probably come up with things like that for, like we could build frameworks for 3-sum and EPSP in the quantum setting as well. For there's an excellent survey by Virginia Williams. You could look at it for these fine-grained reductions. And I would now thank you for the attention, and I'm ready to take questions now.
Thank you very much for a nice talk. We have time for a couple of questions because we started a bit late. I think it's fair to leave some time for questions. So please, if you have any. I will ask a very quick question, which I think is very basic and trivial, but you said at the beginning that you were going to ignore any polynomial factors in this lower bound. Does it mean that when you bring this down to these like polynomial problems, this factor completely disappear, like they don't affect or they become constants?
No, the polynomial factors kind of translate off to logarithmic factors, because the problem size, like the size of the problem changes. So when we are ignoring the polynomial factor in the CNF-SAT problem, we are ignoring like these tiny logarithmic factors in the polynomial problems.
Okay, there is one question. Actually, no, there are two questions. So let me answer. Let me read this one. So Jill Brassard is asking whether there are any non-trivial implications of Q-set without assuming that something is compression oblivious. So can you?
Yes. So like for this or property, okay, but that's kind of a little boring because we already have Q-set conjecture without even defining or property, compression obliviousness. But I would still add, like say for the OR property, we are able to prove that the property is compression oblivious. And using our conjecture, we are able to give better lower bound for orthogonal vector problem, which is non-trivial because it's known that you can solve orthogonal vector. Like if you look at the query complexity of orthogonal vector problem, it is sublinear. So, but I don't have anything for more complex properties, like say parity or majority or anything like that.
Okay, maybe I'll read this last one very quickly and then we move to the next speaker. So Sevag Gariban is asking if you know something about the complexity of deciding whether something is compression oblivious or not, if it's a complete problem, if there is like a trivial upper bound.
I don't understand what it means by a complete problem, but I can just summarize the result that we have. What we prove that for any property which has query complexity, like say the property is defined on capital N bit strings, the query complexity, if the query complexity of the property is strictly greater than root n, we are able to show that this P is not equal to P space. We also make a little more assumption of the property. We assume that the property can be solved in logarithmic amount of polylogarithmic amount of space. But other than that, yeah, that is what we have. And we were also able to show that there exists oracles relative to which Q set is like the basic Q set is valid, but a property is not compression oblivious. So, but that is how much we have for compression obliviousness as of now.
Okay, I think we don't have more time for this question, so I will direct you to discuss it in the Slack channel or privately.
Okay.
I will thank you again for this very nice talk.
Thank you.
And move on to the next. Rize, are you ready to share?
Yes.
Perfect. So our next speaker is Rize Zhang. He's from University of Texas at Austin. And you're going to present about quantum complexity of closest pair, right?
Okay. Hello, everyone. Thanks for the organizer for this wonderful program. And thanks everyone for coming. The title is On the Quantum Complexity of Closest Pair and Related Problems. It's a joint work with Scott Erickson, Nai-Hui Jia, Han-Hsuan Lin, and Xin Wang at UT Austin. Today, I'll tell you how to use the idea of fine-grained complexity in the quantum world. I'll study the closest pair problem and the orthogonal vector problem, and I'll show some positive and negative results about their exact quantum time complexity. So what is the fine-grained complexity? Maybe most of you are more familiar with the NP completeness, which cares about whether a problem can be solved in polynomial or superpolynomial time. For fine-grained complexity, however, it cares about what is the exact exponent, like linear versus n to the 100 time, which makes a huge difference in practice. On the other hand, both NP completeness and the fine-grained complexity are quite similar. One assumes P not equal to NP, and for one of the assumptions in fine-grained complexity is strong exponential time hypothesis. As said in the previous talk, it's basically conjectures that for k set when k is large, the brute force algorithm is nearly optimal. Also, like the CARP and the Cook reduction in NP completeness, fine-grained complexity uses the fine-grained reduction to study the relation between different problems. Here's a picture of fine-grained reduction. Suppose we want to reduce problem P to problem Q. For Scythian instance of problem P, the first step, instance preparation, will construct k instances of problem Q of size n1 to nk, and then the reduction will run the algorithm for problem Q to solve these instances. After that, for the k solutions, the reduction can compute the solution of problem P. If such a reduction exists and the reduction time is less than the lower bound of problem P, then we'll get a lower bound for problem Q. So the main contribution of our paper is first to extend the classical fine-grained reduction to the quantum world, and we introduce the quantum fine-grained reduction and the quantum strong exponential time hypothesis, or QSES. Also, within this framework, we can show that for a closest pair problem in polylogarithmic dimension, which I'll define later, the Groover search is nearly optimal for this problem. Last but not the least, for the positive side, we also give an n to the 2/3 time quantum algorithm for a closest pair problem in constant dimension. Notice that for the n to the 2/3 query algorithm, it can be easily obtained from unbalanced quantum random walk algorithm. But if we want a n to the 2/3 time algorithm, we need to efficiently implement the unbalanced algorithm and use a clever data structure which has a uniqueness property, which it doesn't matter in the classical settings. I'll explain this later in this talk. Let's first consider how fast can we solve k-set problem in quantum. It's easy to get a 2 to the n over 2 time by Google search. Further, Patro et al. In 2005 gives a 1.308 to the n time quantum algorithm for 3-set. Unfortunately, for large K, currently we don't know any quantum algorithm that runs faster than Google search. So it's reasonable to assume that Google search is the optimal quantum algorithm for k-set when k is large. That's what our Q-sets conjectured. Now the question is, can we directly use the Q-sets and some existing fine-grained reductions to get interesting quantum lower bounds? The answer is no, because the classical reductions are no longer fine-grained in quantum world. To illustrate this point, let's see an example. The orthogonal vector problem is given two sets A and B, each contains n Boolean vectors of dimension d. You are asked to decide if there exist two vectors in the set A and B such that their inner product is 0. For this problem, Ren Williams in 2005 shows that under strong exponential time hypothesis, it requires nearly quadratic time to solve when d equals omega log n. So can we prove that under Q sets, a orthogonal vector problem requires nearly linear time in quantum? To answer this question, let's briefly review Williams reduction from CNF set to a orthogonal vector problem. For a CM formula of n variables and m clauses, it first constructs an orthogonal vector instance of size 2 to the n over 2, such that phi is satisfiable if and only if the instance I is the ES instance of a orthogonal vector problem. Since we want to prove that the orthogonal vector problem requires n to the 2 minus epsilon time classically, the reduction time is less than the lower bound of CNF set problem under strong exponential time hypothesis. Therefore, under sets, we get a lower bound for a orthogonal vector problem. If we directly translate it to a quantum version, however, in this time, we can only assume that there's an algorithm for a orthogonal vector problem in quantum that solves this problem in time n to the 1 minus epsilon. So the reduction time now becomes m times 2 to the n over 2, which is larger than the CNF set lower bound under Q sets. So it gives nothing. From this example, we know that the reason why the classical fine-grained reduction doesn't work is that we don't have enough time to write all the input data in the instance preparation step. Fortunately, one of the quantum advantages is quantum query model. Suppose the constructed instance input data can be encoded as the function f. Then we don't need to write down the whole truth table of f as the classical reduction does. Instead, we can just implement an input oracle for this function f, and whenever the algorithm needs some input data and it makes a query, the oracle can just compute this part of input data on the fly, so that if the algorithm can solve the problem without accessing all of the input data, then we can save a lot of time. For instance, many quantum algorithms can query in superposition to reduce the number of queries. By this intuition, we define the quantum fine-grained reduction. And basically, for an instance of problem P, we have an input oracle O of P. The first step is still to construct K instances of problem Q. However, this time, we don't actually write down the input data of these K instances. Instead, we implement K oracles that can simulate the actual input oracle of these K instances. Now, we run the algorithm for problem we run the quantum algorithm for problem Q, and it may make some queries. For each query, our oracle can take some time to simulate the input oracle and returns the answer for to the algorithm. Finally, for the k-solution states, some post-processing like Google search may be required to compute the solution of problem P. For this reduction, if the reduction time is less than the problem P's quantum time lower bound, then we get a quantum time lower bound for problem Q. Let's come back to Williams reduction. We know that the bottleneck is the instance preparation step, which divides the variable of the CNF formula into two sets, XA and XB, and considers all possible half assignments to the variable in these two sets. For each half assignment, we construct a vector that indicates which clauses are satisfied by this half assignment. We can see that this construction is very local, which means the function FA and FB have very succinct representations. For a single vector, it can be computed very efficiently, like a polynomial in n, instead of 2 to the n over 2. Therefore, we can efficiently implement an input oracle for the orthogonal vector problem. For each query index, it returns a Boolean string which corresponds to the vector with this index, and the query cost is just polynomial in n. So that by our quantum fine-grained reduction framework, we now have a quantum time lower bound for a orthogonal vector problem under Q sets. From this example, the take-home message is that if a reduction is local, in other words, the constructed instance input have very succinct representations, then it could be made as a quantum fine-grained reduction. Here's a summary of the results in this work. We studied the closest pair, orthogonal vector, and the bichromatic closest pair problem in constant dimension and the polylog n dimension. We've already shown the quantum lower bound for orthogonal vector problem under Q sets. In the remaining of the talk, I'll focus on closest pair problem. It is defined as follows. Given a set of endpoints in Rd, you are asked to find a pair of distinct points A and B such that their distance is the smallest among all distinct pairs in P. Classically, the most famous algorithm in textbook is the n log n time algorithm by divide and conquer. Further, Guler and Matthias in 1995 gave 2 to the d times n randomized algorithm. For the negative results, Yao in 1989 proved an omega n log n lower bound. Very recently, Karzik and Manugangsi in 2019 improved this result to n to the 2 minus little 1 under strong exponential time hypothesis. What about the quantum complexity of closest pair problem? Let's first consider the quantum lower bound. It's easy to get an omega n to the 2/3 lower bound for a closest pair problem in constant dimension just from the element distinctness lower bound. For the hard part, we prove that in polylog n dimension under Q sets, the lower bound is n to the 1 minus little 1. Here's our reduction. The first step we already shown is from CNF set to a orthogonal vector problem. Then we reduce the orthogonal vector problem to bichromatic closest pair problem, as shown in the picture below. Finally, we reduce the bichromatic closest pair problem to the closest pair problem. For the second step, it is closely related to the Graham-Williams paper. And for the third step, we adapt the proof in KM19 to our quantum fine-grained reduction framework. One thing we need to take care is that in their proof, they construct many closest pair instances, and we do not have enough time in quantum to run the closest pair algorithm for all of them. Instead, we can construct these instances in superposition and use the Google search to find the answer. We can save the reduction time. In this way, we can prove that under Q sets, the closest pair problem in polylog dimension cannot be solved by any quantum algorithm in time n to the 1 minus epsilon for all epsilon greater than 0. Now, let's consider the quantum upper bound for closest pair problem. It's also easy to get an O tilde n time quantum algorithm in polylog dimension just by a Google search, and it is tight by our lower bound. For the constant dimension, we give an n to the 2/3 time quantum algorithm. Let's consider the decision version. Is there a pair within distance epsilon? Note that the query complexity upper bound is easy. We can just consider a random walk over all of the n to the 2/3 size subset. Each step, we have a subset, and we first check whether the current subset contains such a epsilon close pair. And then we randomly replace one element in the subset with another element outside the subset, and we get a new subset. The underlying graph of this random walk is the Johnson graph. Therefore, the quantum query complexity is n to the 2/3. However, from query complexity to quantum time complexity, we need to efficiently implement the quantum walk algorithm. So two factors are very important, U and C, where U is the time cost for taking one step in this random walk, and C is the time cost for checking if the current subset contains the epsilon close pair. So the question becomes, how can we efficiently maintain a set of points that supports 3 operations: add a point, delete a point, and query the minimum distance among the point? Classically, we have some point location data structure like Voronoi diagram or fair split tree. In quantum, however, data structure must be history independent. In other words, for the same data, the memory layout of the data structure should be the same. Otherwise, since we store the data structure into a quantum state for the same subset in the random walk process that comes from different passes, the quantum state will be the different if the data structure do not have history independent property, and the quantum interference will be destroyed. In our paper, we use a radix tree and hash table and a skip list to design such a data structure. And our update time U is polylog n, and the checking time is constant, so that the total running time is about n to the 2/3. Let's summary here. In this talk, I introduced the quantum fine-grained reduction and the quantum strong exponential time hypothesis. And within this framework, we prove some quantum time lower bound for orthogonal vector problem and the closest pair problem. We also gave a quantum algorithm for closest pair problem in constant dimension. Here are some open problems. The first is about a query complexity for orthogonal vector problem. We can just consider this problem as a Boolean function with n times d inputs, and we only support an entry-wise query. We currently only know that for d equals polylog n, the query complexity is n to the 2/3. What about higher dimension, like d is linear in n? Another question is about quantum fine-grained complexity for other problems. Like in the previous talk, they show an omega n to the 1.5 lower bound for added distance based on a different version of Q sets. Can we prove similar results based on our version of Q sets? Also, can we show some quantum fine-grained lower bound for coding problem or lattice problem like CVP or SVP? Thank you for your attention. Any questions?
Thank you very much for a great talk. We already have one question, so we'll go and read it out for you.
Okay.
So Mansur Ziatinov is asking, if you fix k in the Q set fine grained reduction, or if it works for any K. So K, again, the number of instances you create, right?
No, you cannot fix K because in the Q set conjecture, the K is related to the epsilon. But if you fix epsilon, then the K is fixed. So for fixed epsilon, K is constant. But in the reduction, the epsilon is not fixed. It's for any constant epsilon, so K is not fixed.
Let's wait another few seconds. If anyone has more questions, we have time. So there seems there are no further questions. So I will thank you, Gabe, for this great talk.
Thank you.
And I will invite the next speaker to share a screen. Thank you.
Can you hear me?
Yes, I think we can.
Okay.
So
Hi, thanks.
Let me just say a few silly introductions. But so the next speaker is Xichen Zhu from Georgetown University, and you're going to present on approximate degree bounds for K-distinctness. So please go ahead.
All right, thanks for coming. And the topic will be improved approximate degree bounds for K-distinctness. And this is joint work with Nikhil and Justin from Georgetown University. So first, let's introduce what is Quarry complexity. Suppose we have a Boolean function that maps input of length n to -1 or 1, where -1 is true, 1 means false. So the goal is for any input x of length n, we would like to compute f of x by reading as few bits as possible from input string x. And equivalently, it's like computing f of x using an algorithm that invokes the following oracle the least number of times. So here is the oracle that knows the input string x, and it takes input I, and it outputs the ith bit of the input x. And it's worth emphasizing that f is known to the algorithm, and the input x is not known to the algorithm. And in the quantum setting, there's quantum Quarry complexity, and there's a similar quantum oracle where it knows the input x, and it takes input I, and it outputs the ith bit of the string. And so we can define quantum Quarry complexity denoted as Q of f as the minimum number of quantum oracles needed in a quantum circuit to compute f of x with error at most a third. And why we care about Quarry complexity? So there's algorithmic motivation, because most quantum algorithms can actually be phrased as Quarry algorithms, such as Schur's algorithm, Grover search, hidden subgroup, linear system, etc. And it's worth noting that in the Quarry setting, it only cares about the number of queries the algorithm takes. It does not care about the runtime the algorithm takes. But in most cases, it's often the cases that Quarry efficient algorithm can be turned into time efficient algorithm with a little bit extra effort. And this is also illustrated in the previous talk by Rachel. And there's also complexity motivation, because we can use the Quarry complexity to state the power of different computational models, such that we have separations between classical and quantum algorithms. And the problem that we are interested in is called K-distinctness problem. So this is a Boolean function, and the input is that it's given n numbers in a range of size r. Does any number appear more than or equal to k times? So if yes, output -1, otherwise output 1. And for k equals to 2, it is the element distinctness problem. So this is an important function with a long history throughout TCS, and it is well understood. For k greater than 2, it is the quantum query complexity of k distinctness remains open. And it has a connection to finding multi-collisions in hash functions, and which is highly relevant to cryptography. And it's worth noting that k throughout the talk is a constant, unless we explicitly stated otherwise. And so now let me briefly mention the historical results of k distinctness. For k equals to 2, element distinctness problem has been shown to have query complexity equals to theta n to the 2/3. The lower bound was proven by Renes and Shi, and the upper bound was proven by Abinas. For k greater than 2, the first upper bound was proven by Abinas using quantum walls, and later improved by Belov using learning graphs. And for the lower bound, the first lower bound is just the element distinctness lower bound, which was proven by Renes and Shi. And in 2018, Bung, Cathari, and Taylor using polynomial method to improve the lower bound to n to the 3/4 minus 1/2k. And our result, still using polynomial method, is an improvement over BKT's result, where we improve this 1/2k factor to 1/4k. And our lower bound result was the first time to show that fork distinctness is strictly harder than element distinctness. And also our lower bound result also applies to a more general approximate degree setting, which is an interesting topic on its own right, and I will explain this in the next slide. Now let's talk about approximate degree. So first we would like to define epsilon approximation. We say a polynomial P epsilon approximates a Boolean function f if their distance between polynomial P and f is bounded by epsilon for all input string. And we say that the epsilon approximate degree of Boolean function to be the minimum degree necessary for polynomial P to epsilon approximate Boolean function f. And when we set this epsilon to 1/3, this is approximate degree of Boolean function f. And there's a connection between approximate degree and quantum query complexity due to the seminal result by Bill et al. It says that the quantum query complexity of Boolean function is lower bounded by approximate degree of Boolean function. So in order to get the lower bound for quantum query complexity, it's sufficient to get the lower bound for approximate degree. And in our work, we show that the approximate degree of k distinctness is n to the 3/4 minus 1/4k for constant k. So now let's summarize our result. So we have a lower bound result, which is n to the 3/4 minus 1/4k for constant k. And we also have an upper bound result stating for k less than polylog n, the approximate degree is order n to the 3/4. And so now let's deviate a little bit towards our upper bound result. So the previous best result for quantum query complexity of k distinctness is by Belov, which has an exponential factor that depends on k. So for k being a constant, this is not troublesome, but for k greater than log n, this becomes a linear upper bound. And it's worth noting that the approximate degree upper bound does not imply a quantum query complexity upper bound, but at least it implies that a polynomial method that we use cannot yield a better than n to the 3/4 lower bound for quantum query complexity of k distinctness. And one of the reasons that we study the log n distinctness was shown by Li and Wu in 2019. It shows that an upper bound on the quantum query complexity of log n distinctness would imply an upper bound of quantum query complexity of mean entropy estimation. So now let's get back to our lower bound techniques, because our goal is to prove the approximate degree lower bound for k distinctness. And our goal can be summarized in the following sentence. What is the best error achievable by any degree d approximation of Boolean function f? And this can be written in linear programming. So it says, we would like to minimize the error epsilon by searching over all polynomial with a constraint such that the distance between polynomial and Boolean function is bounded by the error epsilon for all input. Meanwhile, the degree of the polynomial is less than or equal to d. And by strong duality of linear programming, this can be written in the dual linear program. And the solution of the dual linear program will give out a degree lower bound for our problem. And let's summarize what previous slide says. It says the epsilon approximate degree of Boolean function f is greater than d if and only if there exists a function psi that maps from Boolean hypercube to real number with the following three conditions. So the first condition says the sum of product between psi and f is greater than epsilon. And we call this high correlation with f because it is like a measure how big part of f is correlating with this psi. And we want this correlation to be as high as possible because that reflects in the primal world so that the polynomial p will have a larger distance with Boolean function f. And the second condition is just the normalization condition. And we need this to make the first condition meaningful. And we call this L1 norm 1. And the third condition is states that psi has zero correlation with any polynomial of degree less than or equal to d. And we give the name the pure high degree of psi is greater than d. And we call this psi a dual polynomial. And however, for the k-distinctness function, it's hard to analyze itself. And BKT identified a more structured composed function, which is OR composed with k-threshold that is identical to k-distinctness. And k-threshold is a function that output false for input of Hamming weight less than k, and otherwise output true. And this superscript is actually a technical factor that, for the purpose of this talk, we can ignore. So what we can say is that instead of proving the approximate degree lower bound for k-distinctness, we can turn our attention to a more structured, simplified function, which is OR composed with k-threshold. And to find the approximate degree for OR composed with k-threshold, we would like to just find the dual witness for this, satisfy the three conditions we mentioned in the previous slide, plus one more condition that arises from this superscript that I will skip throughout this talk. So how did we do that? Well, we alter the dual polynomial. We give a name lambda that is used in BKT's work. So in BKT's work, they decompose this function OR composed with this k-threshold into three-way compositions, OR composed with k-threshold. And they found three dual polynomials for each of the constituent functions, and combine them in a way called dual block composition, which is represented by the star symbol. And the dual block composition is a powerful technique that takes dual polynomials of two different functions and combine them in a manner that give a dual polynomial of composition of the two functions. And recently, this dual block composition has turned out to be a very popular technique to prove the degree lower bound of composed functions. And what we need to show is that the dual composition, lambda, satisfies four conditions: normalization, pure high degree, correlation, and strong dual decay. And for dual block composition, the three conditions are usually preserved: the normalization, pure high degree, and dual decay. So the hard part is for the correlation. The one reason is that the correlation usually does not hold automatically after dual composition. So you have to play around with the dual witness. And it actually rely heavily on psi, the innermost dual, correlating really, really well with the k-threshold function. And by requiring psi to be correlating really well with psi, with k-threshold, would actually hurt the final degree lower bound. So there's an intricate balance between the inner dual witness correlation and the final degree lower bound. And so our solution for that was inspired by Scherzel's work in 2012, which provide a variation of the vanilla dual used in BKT's work. So we attached a polynomial P to the vanilla dual witness in an attempt to improve the correlation. However, we cannot use this P polynomial directly. We have to modify this to account for some refined error notions that arise in the analysis of k-distinctness. And now let me mention some of the open questions related to our work. So since our work heavily was about the degree lower bound, so can we do better than n to the 3/4 minus 1/4k lower bound for k-distinctness? Recall that for quantum Curie complexity, the best upper bound is by Belov. And recently, a work by Liu and Zandrei shows that a search version of quantum Curie complexity of k-distinctness is theta n to the 1/2 minus 1/2 to the k minus 1. So this work might suggest that the right exponent for the degree lower bound might be 3 to the 4th minus 1/exponential of k. But however, we suspect that the technique we used based on dual block composition have reached its limit. So any improvement over 1/4k probably needs some innovative work. And one intermediate goal is just to show that 3 distinctness is harder, strictly harder than 2 distinctness. And we also would like to ask the quantum Curie complexity upper bound for the log-length distinctness. And that's all I have to talk. And I would like to take questions.
Thank you very much for a great talk. We have plenty of time for questions, so I encourage the audience to write them. In the meantime, can I ask you, you mentioned something about the limitations of the polynomial method. Mm-hmm. Could you, like you went over it very quickly. Could you say something about it? Like, is it clear that all these questions you have at the end can be solved using a polynomial method?
Yes. So there's some technical issue with this because we did some modification to the vanilla dual used in BKT by attaching a polynomial P to it. And actually, we have to, by having this polynomial P, we actually need to constrain the degree, the pure high degree of the final dual witness. And actually, by having this P, it constrains us how much mitigation effort it can do for the inner dual correlation, because we need this psi and the k threshold to have very high correlation. And just to go into a little bit detail, so in our work, we allow psi and k threshold to have a little bit to correlate less well compared with BKT's work. And by having them to correlate less well, we also need to mitigate the effect of the final degree lower bound, and by having this P. And there's some balancing effort we need to do. And we found that with this P, the best degree lower bound we can have is by having this 1/4k factor here. And to do 1 over 8K or 1 over 16K, this method actually will break down.
Thanks. It seems that there are no more questions. So I will thank you.
Thank you.
On behalf of all the audience and also thank all the others speaker of the sessions, and have a good rest of the day or of the night, depending on where you are. And see you at the next session.